Tonight, you do not need to understand anything perfectly. You just need to be comfortable and willing to let words drift over you like something soft. And the words tonight are going to be about the strangest, quietest branch of science that human beings have ever wandered into. Let's start with the word itself, quantum. It sounds technical. It sounds like something you would need a whiteboard and 3 degrees to understand. But the word itself is actually quite simple and quite beautiful. A quantum is just a tiny fixed amount of something, a little packet, a single unit that cannot be broken down any further. Think of it like this. If you have a jar of coins, you cannot have half a coin. You cannot have a quarter of a coin. The smallest thing in the jar is 1 coin, and that is it. That is all the word quantum means. The smallest possible chunk of something. A fixed, indivisible little piece. And physics, well, physics is simply the science of how things work, how things move, how things push and pull on each other, how energy flows from one place to another. Physics is the attempt to understand the rules underneath everything, the hidden instructions the universe seems to be following. You do not need to be a scientist to appreciate those rules. You have felt them your whole life. The weight of a blanket, the warmth of sunlight through a window, the way sound travels across a quiet room at night. All of that is physics, the formal study of things you have always already known in your body. So quantum physics, then, is simply the study of the very, very small. Not just small like a grain of sand, not even small like a bacterium. We are talking about scales so tiny that the word small stops feeling like enough. We are talking about atoms, and then the things inside atoms, and then the things that make up those things. At those scales far beyond anything the human eye can reach, far beyond anything any microscope has ever directly seen, the rules change. The familiar rules you grew up with, the rules that govern falling leaves and rolling wheels and boiling water, those rules quietly stop applying. And something else takes over, something stranger, something that took the greatest minds of the 20th century decades to even begin to accept. For most of human history, scientists had a picture of the universe that felt very satisfying. It was the picture of a great machine, orderly, predictable, running according to clear, fixed laws that never bent and never surprised. If you knew the position and speed of every particle in the universe at one moment, the thinking went, you could in principle calculate everything that would ever happen afterward, every falling leaf, every heartbeat, every thought. The universe as a perfect clockwork mechanism, ticking away with absolute precision, following rules set down since the very beginning. It was a beautiful picture in its own way. Reassuring almost, a cosmos that made sense. A reality you could, at least in theory, fully understand. Quantum physics shattered that picture. Not violently, not all at once. It happened slowly, over the first few decades of the 20th century, as careful experiments kept returning results that the old clockwork picture simply could not explain. And gradually, reluctantly, with a great deal of confusion and argument and late nights and letters between brilliant people who could not quite believe what they were being forced to conclude, a new picture emerged. A picture of a universe that, at its smallest scales, is not smooth and continuous and perfectly predictable, but grainy, jumpy, uncertain. A universe that does not always decide what it is until something pays attention to it. A universe built at its foundation, not from tiny solid balls rolling along fixed tracks, but from something far more like flickering possibilities. That is a strange thing to sit with. We will sit with it slowly, over the course of tonight. There is no rush. What is important to understand right now is that this is not just abstract philosophy. Quantum physics is not a theory that lives only in textbooks and university departments. It is the foundation of the world you live in every single day. The screen you may have been looking at before you closed your eyes and put this on, that screen works because of quantum physics. The electricity flowing through it, the way light is produced by it, the semiconductors inside it that allow it to process information, All of that is quantum mechanics made into an object you can hold in your hand. The laser in a barcode scanner at a shop, the solar panels on rooftops converting sunlight into electricity, the MRI machine in a hospital that can look inside the body without cutting anything open. All of these rest on quantum rules. All of them exist because human beings, a little over 100 years ago, began to peer into the very small and found something they never expected. And yet the theory that explains all of this is one that even its inventors found deeply uncomfortable. Max Planck, one of the founders of quantum physics, spent years hoping that his own most important idea was just a mathematical trick, not something the universe was actually doing. Albert Einstein, who contributed enormously to the early development of quantum theory, spent the second half of his life arguing that it could not possibly be the final story, that something was missing, that the universe had to make more ordinary sense than quantum mechanics suggested. Niels Bohr, who perhaps understood it more deeply than anyone, once said that anyone who is not shocked by quantum mechanics has not understood it. These were not confused people. These were the sharpest minds of their century, and the theory left them feeling, on some level, unsettled. That is part of what makes it worth spending a quiet night with. You do not need to resolve anything tonight. That is not what this is for. Tonight is for letting these ideas drift through you, the way music drifts through a room, not demanding to be understood in every detail, just asking to be heard, asking to be felt in some general way. The ideas themselves are not difficult. They are only unfamiliar, and unfamiliar things, when you meet them slowly and quietly, without pressure, have a way of becoming strangely comfortable. So here is where we are. The universe has two sets of rules. The everyday rules, the ones that explain why a thrown ball follows a smooth arc, why a kettle of water heats up slowly and evenly, why the planets move in the paths they move in. Those rules work beautifully at the scale of things you can see and touch. And then there are the quantum rules, the rules that take over at scales far smaller than anything visible, rules that are different in almost every way from the everyday ones, rules that allow things to be in two places at once, rules that say the act of looking at something changes what it is, rules that mean two particles can be connected across any distance at all, rules that are, in a word, strange, but strange in a way that is deeply, quietly beautiful once you begin to sit with them. We are going to walk through all of it tonight. Slowly, with no pressure and no examination at the end. We will begin with the atom, the thing that started all of this, and we will follow the thread all the way through to the deepest layer of reality that physics has yet reached. And we will do it the way this kind of thing deserves to be done. Unhurriedly, with long pauses built in, with the understanding that the point is not to memorize or analyze. The point is simply to be in the presence of something genuinely extraordinary. The hidden instructions of the universe, the rules underneath everything, the quiet, strange, beautiful machinery, if you can even call it machinery, that holds you and everything around you together. You are lying somewhere comfortable right now. You do not have to do anything. Just breathe and listen and let the smallest things in the universe do what they have always done, exist in their uncertain, flickering, quietly miraculous way, all around you and inside you and between every word. Everything you can touch is made of atoms. The pillow beneath your head, the blanket resting on your body, the air moving slowly in and out of your lungs right now. All of it, every single bit of physical matter in the world you have ever encountered, is made of atoms. Tiny, unimaginably small units of matter, packed together in different arrangements to make everything that exists. The wood in a tree, and the iron in your blood, and the water in a glass, and the glass itself. All atoms, just arranged differently, bonded differently, vibrating at different speeds. Everything you have ever touched has been a collection of these tiny things, pressing against another collection of these tiny things. And for almost all of human history, nobody knew. For thousands of years, people looked at the world and had no idea, that underneath all the surfaces and textures and colors, there was this hidden layer. The ancient Greeks had a word for it, atomos, meaning something that cannot be cut, something indivisible, the smallest possible piece. But it was a philosophical idea, not a scientific one. There was no way to test it, no way to see. It was just a thought, a guess about the nature of things, made by people sitting and thinking in a world that had no microscopes, no laboratories, no instruments sensitive enough to reach that far down. So the idea drifted through history, sometimes accepted, sometimes forgotten, never proven. It was not until the early 1800s that someone began to put real evidence behind it. A quiet English schoolteacher named John Dalton spent years studying how chemical substances combine with each other. He noticed patterns. He noticed that when elements joined together to form compounds, they always did so in fixed whole number ratios, not random amounts, not approximate amounts, precise, repeating ratios that suggested the substances were made of individual countable units. Dalton proposed that each element was made of its own kind of atom, that atoms of different elements had different weights, that chemical reactions were simply atoms rearranging themselves into new combinations. It was a careful, measured idea, not flashy, not dramatic, just a scientist looking at patterns and following them to their logical conclusion. But even Dalton thought atoms were the end of the story. Tiny, solid spheres, each one whole and unbreakable, the smallest things that existed. That picture held for most of the 19th century. And then, near the very end of it, something happened that changed everything. A British physicist named J.J. Thomson was experimenting with electricity in 1897. He was passing electrical current through a glass tube with most of the air pumped out of it, a device that produced a faint glowing beam, which scientists at the time called a cathode ray. Thomson noticed that this beam could be bent by electric and magnetic fields, and he began to measure it carefully. What he found was that the beam was made of particles, tiny, negatively charged particles, far smaller than any atom. He had found the electron, a piece of the atom, something inside the atom, which meant atoms were not solid and indivisible after all. They had parts. This was the first hint that the world went deeper than anyone had thought, that the bottom kept moving further down. Thomson imagined the atom as something like a pudding, a soft, spread-out ball of positive charge, with electrons embedded in it like raisins scattered through a bun. It was a reasonable guess given what he knew, and for about a decade, it was the accepted picture. Then a New Zealand physicist named Ernest Rutherford decided to test it. In 1909, working in Manchester, Rutherford set up one of the most elegant experiments in the history of science. He took a thin sheet of gold foil, gold because it can be beaten into sheets just a few atoms thick, and he aimed a beam of tiny, positively charged particles at it. These particles were called alpha particles, and they were relatively heavy and fast. The expectation, based on Thomson's pudding model, was that they would pass through the gold foil with only very slight deflections. The positive charge was supposed to be spread out evenly through the atom, like a soft fog. The alpha particles would push through it gently, barely disturbed. What actually happened was not that. Most of the alpha particles did pass straight through, just as expected, but some of them, a small number, deflected at very large angles, and a few of them bounced almost directly backward. Rutherford later said it was as if he had fired artillery shells at tissue paper and they had bounced back and hit him. He could not explain it with the pudding model. Soft, spread-out positive charge could not bounce a heavy, fast particle backward like that. Something concentrated, something dense, something very small and very hard at the center of the atom. That was the only thing that could explain it. Rutherford concluded that the atom had a nucleus, a tiny, incredibly dense core, carrying almost all of the atom's mass, packed into a space unimaginably smaller than the atom itself. And around this nucleus, far out in what amounted to empty space, the electrons moved. The image that comes from this is one of the most quietly astonishing in all of science. If you took a single atom and expanded it until its nucleus was the size of a grain of sand sitting on the center circle of a football pitch, the electrons would be somewhere in the stands. Everything in between would be empty, pure, open, vacant space. The atom, the supposedly solid building block of all matter, is almost entirely nothing, which means that you, lying there right now, are almost entirely nothing. Every atom in your body is mostly empty space. The hand resting on the blanket itself, the mattress underneath, all of them almost entirely void, with tiny specks of matter separated by vast distances, relatively speaking. The reason your hand does not pass through the blanket is not because matter is solid in the way it feels. It is because of electromagnetic forces. The electrons in your hand and the electrons in the blanket repelling each other, pushing back, creating the sensation of resistance that the mind understands as solid. Touch is not matter meeting matter. It is force meeting force. Let that settle for a moment. There is no rush. So we have the atom, a nucleus at the center, electrons somewhere out in the surrounding space. Rutherford imagined the electrons orbiting the nucleus the way planets orbit the sun. Circular paths, stable, predictable. It was a natural image to reach for, and it is still the image that appears in textbooks and logos and diagrams everywhere you look. But it was wrong, or rather, it was not deep enough. Because if you apply the physics that was known in 1911 to an electron orbiting a nucleus like a tiny planet, something troubling happens. A charged particle moving in a curved path should radiate energy. It should constantly be losing energy in the form of light, which means it should be spiraling inward, losing speed, getting closer and closer to the nucleus, and within a tiny fraction of a second, crashing into it. By the known physics of the time, atoms should not be stable. They should collapse almost instantly. Matter should not hold together. You should not exist. And yet, plainly, you do. Atoms are stable. Matter holds together. Something was protecting the electrons from spiraling in. Something was keeping them at their distances. And whatever that something was, it was not in any rulebook that physics had written yet. This was the problem waiting at the edge of everything in the early 20th century. The atom had been found. Its structure had been roughly sketched, but the sketch had a contradiction built into its heart, and resolving that contradiction would require a completely new kind of physics, a physics of packets and jumps and probabilities, a physics where the old smooth clockwork rules simply did not apply. That is where we are headed, not tonight in one step, but gently, one idea at a time. For now, just rest with the image of the atom as it truly is. Not a solid little ball, not a tiny marble, but an almost entirely empty space, with a speck of dense matter at its center, and electrons existing somewhere in the surrounding void, not quite where you would expect, not quite doing what the old rules said they should, waiting to reveal a stranger truth. The universe goes deeper than the surface. It always has. And the deeper it goes, the quieter and stranger and more beautiful it becomes. There is a particular kind of glow that comes from something very hot. You have seen it without perhaps ever thinking much about it. The orange coil of an electric heater in a dim room, the red heart of a fire burning low, the white brightness of molten metal being poured in a foundry. As something heats up, it begins to glow. First a deep, dark red, then a brighter red, then orange, then yellow, then, at extreme temperatures, a blinding blue-white. The color changes as the temperature changes, in a smooth and consistent way, the same every time, with every material. It does not matter whether you are heating iron or copper or glass. Heat anything enough and it moves through the same sequence of colors. This was a well-known fact by the late 1800s. Scientists had measured it carefully. They had charted it, they had named it. What they could not do was explain it. The physics of the time, the accumulated wisdom of 2 centuries of careful work, could not produce an equation that matched what was actually observed. The mathematics kept going wrong in the same place. At the high-frequency end of the spectrum, the short wavelengths, the blue and violet and ultraviolet end, the equations predicted something that could not possibly be true. They predicted that a hot object should radiate infinite energy. Not a lot of energy, not more energy than expected. Infinite, an endless, impossible flood of energy pouring out at high frequencies from any object with any temperature above absolute zero. Every warm thing in the universe should be blazing with infinite ultraviolet radiation, which was plainly not happening. You could hold your hand near a warm cup of tea without being destroyed by an infinite burst of high-frequency light. The equations were wrong. Something in the foundations of the physics was wrong. This problem had a name. Scientists called it the ultraviolet catastrophe. It sat there, unresolved, making careful physicists quietly uncomfortable through the final years of the 19th century. And then, in the year 1900, a German physicist named Max Planck found a way through it. Planck was 42 years old, methodical, deeply serious, not the kind of person who liked overturning established ideas. He had spent years working on this problem. He had tried every approach the existing physics offered. None of them worked. And so, in something closer to desperation than inspiration, he tried something that had no real justification behind it, something that felt, to him, like a trick. He assumed, just as a mathematical device, just to see what would happen, that energy could not be radiated in a continuous smooth flow. He assumed that it had to come in fixed, indivisible packets, tiny chunks of a specific size, each chunk determined by the frequency of the light being emitted. High-frequency light would come in larger chunks, low-frequency light in smaller ones. And the chunks could not be subdivided. You could emit 1 chunk, or 2 chunks, or 3, but never 1.5, never 2 1/3. Always whole numbers of these tiny fixed packets. He called each packet a quantum, from the Latin word for amount, a fixed minimum quantity. And when he put this assumption into his equations, the mathematics worked. The predicted curve matched the observed curve perfectly, at every frequency, including the high end that had defeated every other approach. The ultraviolet catastrophe disappeared. The equations no longer predicted infinite energy. They predicted exactly what experiments had measured. It was one of the most precise matches between theory and experiment in the history of physics. Planck announced his result in December of 1900, and then, by his own later admission, he spent years trying to find a way to make it go away. Not because the mathematics did not work, it worked perfectly, but because the idea behind it was deeply uncomfortable. Energy coming in fixed packets felt wrong. It felt like a violation of everything physics had built itself on. The whole framework of classical physics assumed that quantities in nature varied smoothly and continuously. You could have any amount of energy, any amount at all. You could always divide a quantity in half, and then in half again, and there was no floor, no minimum, no smallest chunk you could not go below. Nature was continuous. That was not a guess. That was a foundational assumption so deeply embedded that most physicists had never thought to question it. Planck was questioning it, or rather, his mathematics was questioning it, and he could not quite bring himself to fully believe what his own equations were telling him. He hoped that the quantization was just a feature of the mathematics, not of reality itself, a useful fiction, a calculating trick that happened to give the right answer without actually describing how the world worked. He was wrong to hope that. The packets were real. It would take several more years and the work of a young patent clerk in Switzerland for that to become undeniable. But for now, in 1900, the idea existed. It was out in the world, and even if Planck himself was not sure what to make of it, the idea was not going back. What does it actually mean, this quantization of energy? Let us stay with it for a moment, because it is one of those ideas that seems simple on the surface and keeps revealing new depth the longer you sit with it. Think about a ramp and a staircase. If energy were continuous, if it flowed in smooth, unbroken streams, then moving from one energy level to another would be like walking up a ramp. You could be at any height, any point between the bottom and the top, a smooth, uninterrupted progression from less to more. But quantized energy is not a ramp, it is a staircase. You can be on the first step, you can be on the second step, you can be on any step, but you cannot be between steps. There is no in-between, there is no halfway. You jump from one step to the next, and the space between the steps is not a place you can exist. This is how energy works at the quantum level. A particle does not ease its way from one energy state to another the way a ball rolls gradually down a slope. It jumps, instantly, from one allowed level to another, with nothing in between. The jump is called a quantum leap, a phrase that has entered everyday language to mean a large dramatic change, which is somewhat ironic because the actual quantum leap is the smallest possible change, the minimum amount of change the universe permits. Planck had found a constant in his equations, a number that set the size of the packets, a fixed relationship between the frequency of radiation and the energy of each quantum. This number is now called Planck's constant, and it is one of the fundamental numbers of the universe. It is extraordinarily small, vanishingly, almost incomprehensibly small, which is why we do not notice the graininess of energy in everyday life. The steps on the staircase are so tiny, so close together, that at human scales they blur into something that looks and feels exactly like a smooth ramp. It is only when you zoom in to the scale of atoms and electrons that the steps become visible, that the jumps become undeniable, that the ramp reveals itself to have been a staircase all along. There is something quietly profound in that. The smoothness of the everyday world is an illusion of scale. Not a deception exactly. The smoothness is real enough at the level you live at, but underneath it, at a level you will never directly see, the universe is counting. Whole numbers only. 1 quantum, 2 quanta, 3. The universe deals in discrete packets, and has been doing so since long before there was anyone around to notice. Planck spent the rest of his career as one of the most respected physicists in the world. He won the Nobel Prize in 1918 for his discovery. And yet, by many accounts, he remained somewhat ambivalent about what he had done. He had opened a door he had not intended to open. He had introduced an idea that would, in the hands of younger physicists, completely dismantle the classical picture of the universe. He had wanted to fix a single problem in the theory of heat radiation. Instead, he had planted a seed that would grow into the most radical transformation in the history of physics. That is sometimes how the deepest changes happen, not with a grand announcement, not with someone declaring that everything is different now, but with a quiet, reluctant calculation, a number that works, a trick that turns out not to be a trick at all, an answer that arrives before anyone is quite ready to accept what it means. And lying somewhere in that answer, waiting to be drawn out over the following decades, was everything. The nature of light, the structure of the atom, the behavior of electrons, the reason matter holds together, the foundation of every technology that would define the century to come. All of it folded inside one small, uncomfortable idea, proposed by a careful German physicist who mostly just wanted the mathematics to behave. Energy comes in packets, the universe counts, and nothing after 1900 would ever look quite the same again. Close your eyes for a moment and think about light, not the harsh light of a screen or a fluorescent tube, but something gentler. The last of the evening sun coming through a curtain, the soft glow of a lamp in a quiet room, the way light falls across a surface and makes it look warm. Light is so familiar that it barely seems worth thinking about. It is just there, the way air is just there. We move through it all day without ever really wondering what it is. But what it is turns out to be one of the strangest questions in all of physics. And the answer, or rather, The two answers that somehow have to be true at the same time is one of the places where the quantum world first shows its most unsettling face. For most of the 19th century, physicists were confident they knew what light was. It was a wave, a ripple moving through the electromagnetic field, the way a ripple moves across the surface of still water when you drop something into it. The evidence for this was overwhelming. Light bends around corners, slightly, in a way that only waves do. When two beams of light overlap, they create interference patterns, bright bands where the waves reinforce each other, dark bands where they cancel each other out. This is exactly what you would expect from waves, and exactly what you would not expect from particles. Particles do not cancel each other out when they meet. They collide, or they pass, but they do not create dark bands of absence. The wave picture of light was confirmed by experiment after experiment. It was as solid as anything in physics. And then something came along that the wave picture could not explain. It was called the photoelectric effect, and on the surface it sounded simple. Shine light onto certain metals, and electrons get knocked off the surface. The light goes in, electrons come out. This in itself was not surprising. Light carries energy. Electrons can be freed if they absorb enough energy. That much made sense. The surprising part was in the details. The details that the wave picture of light simply could not account for. Here is what the wave picture predicted. If you shine brighter light onto the metal, more intense light, more energy coming in, you should knock off more electrons, and knock them off with more energy. Turn up the brightness, turn up the effect. That is what waves would do. More wave, more push. And here is what actually happened. Brightness made almost no difference to the energy of the electrons that came off. What mattered was the color of the light, the frequency, the pitch of the light wave, if you want to think of it that way. Low-frequency light, red light, infrared, knocked off no electrons at all, no matter how bright you made it. You could flood the metal with red light all day and nothing would happen. But high-frequency light, blue light, ultraviolet, knocked electrons off immediately, even at very low brightness. And the energy of each electron that came off depended only on the frequency of the light, not on how much of it there was. This made no sense if light was a wave. A more intense wave carries more energy, spread out continuously across its surface. More wave, more energy delivered to the electrons. That is how waves work. But that is not what was happening. In 1905, a 26-year-old patent clerk in Bern, Switzerland, working in his spare time, wrote a paper that explained it. His name was Albert Einstein, and this paper, not his work on relativity, but this one, about light and electrons, is the paper that would eventually win him the Nobel Prize. Einstein reached back to Planck's idea from 5 years earlier, the idea that energy comes in fixed packets, in quanta, and he extended it in a way that Planck himself had not been willing to go. Einstein proposed that light itself is made of packets. Not just that light energy is exchanged in chunks as a kind of mathematical convenience, but that light genuinely, physically travels as a stream of individual particles. Each particle carries a fixed amount of energy determined by its frequency. High-frequency light, blue, violet, ultraviolet, comes in high-energy packets. Low-frequency light, red, infrared, comes in low-energy packets. These particles of light would later be named photons. With this idea, the photoelectric effect made perfect sense. Each electron in the metal needs a certain minimum amount of energy to be knocked free. If a photon carries that much energy or more, it knocks an electron loose. If it does not carry enough, the electron stays put, no matter how many of these low-energy photons arrive. It is not about the total amount of light. It is about the energy of each individual packet. A flood of low-energy packets still cannot free an electron that needs a high-energy packet to break it loose, just as 1,000 gentle taps cannot do what one firm knock can do. This explained everything the wave picture could not. But it created a problem that, in some ways, was even larger than the one it solved. Because light was a wave. That was not in doubt. Decades of careful experiments had proven it beyond any reasonable question. Interference patterns, diffraction, the bending of light around edges, all of it pointed to waves, unmistakably. And now Einstein was saying light was also made of particles, individual, countable, discrete little packets of energy, each one a photon, both things at once. Wave and particle, simultaneously, in some way that the existing picture of reality had absolutely no room for. This is called wave-particle duality, and it is not a contradiction that was eventually resolved and neatly tidied away. It is a permanent feature of quantum reality. Light is a wave, light is a particle. Which one it appears to be depends on how you look at it, on what kind of experiment you do, on what kind of question you ask. Ask it a wave question, and it answers as a wave. Ask it a particle question, and it answers as a particle. But it is never just one or the other underneath. It is always both. This bothered people enormously. It still bothers people, if they think about it carefully enough, because our minds are built for the everyday world, where things are either waves or particles and never both, where a thing is what it is, regardless of how you look at it. We do not have a good intuitive category for something that shifts its fundamental nature depending on how you approach it. And yet that is what light does. That is what, as it would turn out, every quantum object does. Think for a moment about what a photon actually is. A single particle of light, one quantum of electromagnetic energy, the smallest possible amount of light that can exist. When you sit in a sunlit room, billions upon billions of photons are landing on your skin every second, each one carrying its small packet of energy, each one a thing that is somehow both a wave rippling through a field and a particle arriving at a specific point. The warmth you feel is the accumulated arrival of countless individual photons, each one giving up its energy to your skin. The color you perceive depends on the frequency of those photons, the energy each one carries, translated by the cells in your eyes into something your brain experiences as red or blue or gold. The light that falls across a quiet room in the evening is not a smooth, unbroken river of illumination. It is a rain of individual particles, each one a tiny packet of pure energy, each one carrying its color coded into its very existence, each one traveling at the same extraordinary speed, the fastest anything in the universe can travel, until it meets a surface or an eye and gives up what it carries. And each one of those particles is also a wave, rippling outward from its source, spreading through space, capable of interfering with other waves, capable of bending around corners, capable of producing the shimmering patterns of light and dark that you sometimes see when sunlight passes through a narrow gap. Both things, always both things. Einstein spent years after 1905 sitting with what he had done. He had confirmed Planck's instinct and gone further. He had made the quantum real, not a mathematical trick but a physical fact. Light was made of particles, and he was not entirely comfortable with where that led. The deeper implications of the quantum world that his own paper had helped to build would later become the source of his greatest scientific disagreements. He spent decades arguing that quantum mechanics could not be the final answer, that something calmer and more orderly had to be underneath it. But the photon was real, the duality was real. The rain of light falling through a window, each drop a particle and a wave, was real, and the physics that would follow from that reality would be stranger than almost anyone, including Einstein, was prepared for. For now, though, just rest with the image. The light in the room where you are lying, or the darkness, if all the lights are off, is a quantum phenomenon. Every photon that reached your eyes today was a tiny packet of energy that also traveled as a wave. Something that defies any simple picture, something that the universe does not feel obliged to make easier to understand just because we find it confusing. The universe is not built around our comfort, it is built around its own rules. And one of those rules, apparently, is that light gets to be two things at once. Let that be enough for now. You do not need to resolve it. Nobody has. Just let the idea rest alongside you, in the quiet, while the photons that make up whatever dim light remains in your room continue doing exactly what they have always done. Being both, refusing to choose, traveling at the speed of light toward whatever surface will receive them. There is one experiment that physicists return to again and again when they want to show someone the heart of quantum mechanics. Not because it is the most technically complex, not because it requires the most sophisticated equipment, but because it is the place where the strangeness of the quantum world becomes impossible to explain away, impossible to soften, impossible to make ordinary. Richard Feynman, one of the greatest physicists of the 20th century, said that this single experiment contains the only real mystery of quantum mechanics, that everything else in the quantum world, however strange it seems, is in some way a variation on what happens here. He said that nobody understands it, not really, not all the way down, and he meant that as a precise statement, not a poetic one. The experiment is called the double slit experiment, and the setup is almost childishly simple. Imagine a barrier, a flat surface with two narrow slits cut into it, side by side, close together. Behind the barrier, some distance away, is a screen, something that records where particles land, lighting up or leaving a mark at each point of impact. In front of the barrier, a source that fires particles, electrons, photons, it does not matter which, one at a time, aimed at the barrier. That is the whole setup. A source, a barrier with two slits, a screen. Now, before we talk about what actually happens, think about what you would expect to happen. If electrons are particles, tiny little bullets, as physicists once imagined them, then the pattern on the screen behind the barrier should be simple. Some electrons will hit the barrier and stop. Some will pass through the left slit. Some will pass through the right slit. And on the screen behind, you would expect to see two bands of marks. One behind the left slit, one behind the right slit. Two bright stripes where the electrons piled up and darkness everywhere else, like firing paint pellets at a wall through two narrow gaps, two stripes of paint, clean, simple, exactly what you would expect from particles. That is not what happens. What appears on the screen is not two bands. It is many bands, a series of alternating stripes, bright, dark, bright, dark, bright, spreading out across the screen in a pattern that physicists immediately recognized. It is an interference pattern, the same kind of pattern you get when two sets of waves overlap. When waves from two sources meet, they add together where their peaks coincide and cancel each other out where a peak meets a trough. The result is a regular pattern of reinforcement and cancellation, bright where the waves add up, dark where they cancel. This is a wave phenomenon. Bullets do not do this. Particles do not do this. Only waves produce interference patterns. So the electrons, somehow, are behaving like waves. Each electron, passing through the two slits, seems to spread out like a wave, pass through both slits simultaneously, interfere with itself on the other side, and land on the screen according to the resulting interference pattern. Not like a bullet going through one gap or the other. Like a ripple spreading through both gaps at once and overlapping with itself. This is already strange, but it is about to get stranger, because the experiment works even when you fire the electrons one at a time. One electron, then another, each one fired individually, with time in between. No two electrons in the apparatus simultaneously, no way for one electron to interfere with another. And yet, over time, as the individual electrons accumulate on the screen, the pattern that emerges is still the interference pattern, still the multiple bands, still the alternating bright and dark stripes, as if each individual electron somehow knows about both slits, as if each individual electron travels through both slits at once and interferes with itself. As if each electron, alone in the apparatus, is a wave that spreads through all available space, passes through both openings, and only becomes a particle again when it lands on the screen. One electron, two paths, both taken at once. Sit with that for a moment. There is no need to rush past it. Now comes the part that troubled physicists most deeply. The part that Richard Feynman was pointing to when he said, "Nobody truly understands this." Because a natural question arises from everything described so far. If the electron really is going through both slits at once, can we simply check? Can we put a detector at one of the slits, something sensitive enough to register when an electron passes through, and find out which slit it actually used? The answer is yes. You can do this. The technology exists. You can place a detector that will tell you, for each electron, whether it went through the left slit or the right slit. And when you do, the interference pattern disappears. Not partially, not slightly, completely. The moment you add a detector that tells you which slit each electron went through, the screen behind the barrier stops showing the interference pattern and starts showing exactly what you would expect from particles. Two bands, one behind each slit. The electrons, now that they are being watched, behave like bullets. They go through one slit or the other. They land in two stripes. They are ordinary, predictable, classical little particles. Remove the detector, stop watching, and the interference pattern comes back. The act of observation changes the outcome. Not because the detector physically disturbs the electron in some clumsy mechanical way that ruins the experiment. Physicists have thought about this very carefully. They have designed versions of the experiment where the disturbance from measurement is as small as it could possibly be. It does not matter. The result is the same. Knowing which slit the electron went through, even in principle, even if you never look at the detector's record, destroys the interference pattern. Not knowing allows it. The electron behaves differently depending on whether information about its path exists anywhere in the universe. Not just whether a human being looked at it, whether the information exists at all, whether anything, anywhere, in any form, recorded which way it went. If such a record exists, the electron is a particle. If no such record exists, the electron is a wave. Reality, at the quantum level, seems to depend on what is known. This is not a flaw in the experiment. This is not a limitation of the equipment. This has been tested in laboratories around the world, many times, with increasing precision and care. The result is always the same. The double-slit experiment does exactly this, reliably, every time. It is not a curiosity or an anomaly. It is a window into how things actually are. Think about what this implies. Before you put the detector in, the electron has no definite path. It is not secretly going through the left slit while appearing to go through both. It genuinely has no fact of the matter about where it is until it is measured. It exists in a kind of spread-out, undefined state, a superposition of all the paths it might take, and the interference pattern is the physical evidence of that superposition. The wave pattern is the electron's uncertainty made visible. But the moment information is created about its path, the moment a measurement happens, the moment the universe acquires a record of where the electron was, all those possibilities collapse into one. The electron had been everywhere it might have been. Now it is somewhere, and that somewhere is all it ever was. It is as if the act of asking a question forces the universe to pick an answer, and before you ask, there is no answer. There is only the quiet hum of all possible answers, coexisting, waiting. This is not philosophy. This is what the mathematics of quantum mechanics describes, and what experiment after experiment confirms. The quantum world is not a world of things with hidden definite properties that we simply have not measured yet. It is a world where the properties do not exist in definite form until they are measured. Where reality, at its most fundamental level, is made not of fixed facts but of possibilities. Where the boundary between what is observed and what is real is not clear the way we always assumed it would be. Nobody has fully resolved what this means. Physicists have proposed many interpretations, many ways of making sense of the mathematics philosophically, and none of them has won the argument. The experiment sits at the center of quantum mechanics like a koan, a question that the physics answers precisely and the mind cannot quite absorb. You can calculate everything about it perfectly. You can predict the pattern on the screen to extraordinary accuracy. And yet the question of what is actually happening, where the electron actually is while it is in flight, what it means for a single particle to go through two slits at once, remains, in some sense, open. Feynman was right. It is the only real mystery. And it is a mystery not because we have not looked carefully enough, but because looking is the very thing that changes what there is to see. For now, though, you do not need to carry this as a problem to be solved. Let it rest the way the electron rests, spread out across all its possibilities, uncommitted, undefined, until the morning comes and the questions of the day make their demands again. For tonight, it is enough to know that the universe at its smallest level holds its options open, that it does not decide until it must, that there is something in the nature of things, far below the surface of the world you can touch, that resists being pinned down, that keeps its possibilities alive until the last possible moment. There is something almost restful in that, if you let it be. The universe, in its deepest nature, is not rigid or fixed or fully determined. It is open, probabilistic, full of paths not yet taken and outcomes not yet chosen. And tonight, in the quiet, that openness surrounds you in every atom of the air you are breathing. There is a word that gets used a great deal when people talk about quantum mechanics. It gets used in films and in popular books, and in conversations where someone wants to sound as though they understand something mysterious. The word is superposition. And like most things that get borrowed from physics and used loosely in the wider world, the real meaning is both simpler and stranger than the way it usually gets discussed. Tonight we are going to sit with what it actually means, not the version dressed up for effect, the real thing as quietly and as carefully as we can. Superposition at its heart is simply this. A quantum particle can exist in multiple states at the same time, not flickering rapidly between them, not secretly in one of them while we just do not know which. Genuinely, physically, in multiple states simultaneously, until a measurement is made, at which point it settles into one. That is superposition. A particle holding several possibilities open at once, like a question that has not yet been answered. To feel your way into this idea, start with something familiar. Imagine a coin being flipped. While it is spinning in the air, tumbling end over end, it is not heads and it is not tails. In a loose, everyday sense, you might say it is both. Both outcomes are possible. Neither has been decided yet, and something about the spin contains both possibilities at once. When the coin lands, it becomes one thing, heads or tails. The spinning stops, the possibilities collapse into a single outcome, and that is what the coin is from that moment on. The quantum version of this is not quite the same. A spinning coin is still secretly either heads or tails, just moving too fast to tell, but as an image to hold in mind, it carries some of the right feeling. The sense of genuine openness, of multiple outcomes coexisting in the same moment, of something becoming definite only when the spinning stops. In quantum mechanics, the most commonly discussed form of superposition involves a property of particles called spin. Spin is a quantum property that has no perfect everyday equivalent, but the closest analogy is to imagine a tiny magnet. A particle with spin behaves as though it has a magnetic axis, pointing either up or down relative to some direction you choose to measure. When you measure the spin of an electron along a particular axis, you always get one of two results, up or down, nothing in between. Spin, like energy, is quantized. It comes in one of two values, and those are the only options. But here is the quantum part. Before you measure, the electron is not in the spin-up state, and it is not in the spin-down state. It is in a superposition of both. Both spin states exist simultaneously in the same particle, weighted by probabilities that the mathematics of the wave function describes precisely. The spin does not have a value before measurement. It has a range of possibilities, held open, waiting. And when you measure, the superposition resolves. The particle becomes spin up or spin down, with probabilities that quantum mechanics predicts exactly. But the choosing happens at the moment of measurement, not before. This is the thing that troubled Einstein most deeply. He felt, with great force for many years, that this could not be the whole story. That the particle must already have a definite spin before you measure it, even if you do not know what it is. That quantum mechanics was like a weather forecast that tells you the probability of rain without knowing the actual state of every air molecule. Useful, but not fundamental. That underneath the probabilistic surface of quantum mechanics, reality was still definite and determined, just hidden from view. He called this idea, in various forms, the belief in a complete description of reality, a reality that exists fully and definitely, whether or not anyone is looking. Experiments done decades after Einstein's death showed that he was wrong about this. The particle does not have a hidden definite spin before measurement. The superposition is real. The indefiniteness is not a gap in our knowledge. It is a feature of the particle itself. Reality at the quantum level is genuinely, irreducibly probabilistic, not just unknown, undecided. Now we come to the most famous illustration of superposition, the one that has escaped from physics textbooks into everyday conversation, the one that involves a cat. In 1935, the Austrian physicist Erwin Schrödinger, whose equation for the wave function we mentioned earlier, and whose contribution to quantum mechanics is second to almost none, wrote a paper in which he described a thought experiment. He was not proposing this as something to actually do. He was making a philosophical point, with characteristic sharpness. He wanted to show how strange the implications of quantum superposition became when you tried to apply them to objects larger than particles. Imagine a sealed box, he said. Inside the box is a cat. Also inside the box is a small amount of a radioactive substance, connected to a device containing a vial of poison. Radioactive decay is a quantum process. It happens according to quantum probabilities, with no way to predict exactly when a particular atom will decay. If the radioactive atom decays, the device triggers, the vial breaks, and the cat dies. If the atom does not decay, the cat lives. Now, according to quantum mechanics, the radioactive atom is in a superposition of decayed and not decayed states until it is measured. If the atom is in superposition and the cat's fate is tied directly to the atom, then what is the cat? By the strict logic of quantum superposition applied to the whole system, Schrödinger said, the cat would be in a superposition of alive and dead. Neither alive nor dead, both simultaneously, until someone opens the box and looks. Schrödinger found this conclusion absurd. He was not presenting it as a delightful feature of quantum mechanics. He was presenting it as a reductio ad absurdum, a sign that something in the interpretation of quantum mechanics had gone wrong, that the rules of the quantum world could not simply be extended without modification to everyday objects like cats. He meant the thought experiment as a criticism. And yet, in a curious reversal, the image he created to criticize quantum mechanics became one of its most famous icons. Schrödinger's cat is now used more often to illustrate superposition than to question it. The image stuck, the cat in the box, neither alive nor dead, waiting for the box to open. Whether or not macroscopic objects, cats, tables, planets, can genuinely be in superposition is one of the deep open questions in the foundations of quantum mechanics. At the scale of atoms and electrons, superposition is unambiguous and experimentally confirmed. At the scale of everyday objects, something happens, physicists call it decoherence, where the quantum superposition becomes overwhelmingly fragile, collapsing almost instantly due to the constant interaction of large objects with their environment. In practice, a cat cannot be in a superposition of alive and dead because it interacts with too many other things too quickly for the superposition to survive. But the question of where exactly the quantum world ends and the everyday world begins, where superposition gives way to definite states, is not fully answered. It is called the measurement problem, and it sits at the center of quantum foundations like a quiet, persistent puzzle that 100 years of brilliant work has not fully resolved. There is something worth sitting with in the idea of superposition, beyond the puzzles it raises. There is a kind of generosity in it, if you approach it from a certain angle. The quantum world, before measurement, holds everything open. It does not commit prematurely. It carries all the possibilities with it, each one weighted, each one real in its own way, until the moment arrives when the universe must choose. There is no rushing. There is no decision before the decision is needed. Just the quiet coexistence of all that might be, and perhaps that is something to carry gently into sleep. The deepest layer of reality is not rigid or forced into a single fixed state. It holds possibilities. It stays open. It carries more than one answer at a time and waits until the last possible moment to commit. Physicists have been arguing about what this means for 100 years. They have not agreed. And that is perfectly fine. Some of the most important things in the universe do not come with agreed-upon explanations. They come with mathematics that works, and experiments that confirm it, and a deep, unresolved quiet at the center of it all. You do not need to resolve it either. You can simply rest in the knowledge that at the very smallest scales of the world around you and inside you, particles are doing what they have always done, holding their options open, existing in their quiet superpositions, carrying every possibility at once until the universe pays attention, and in the meantime, everything continues. The atoms hold together, the world coheres, the blanket stays warm, all of it humming along perfectly, even with this unresolved mystery sitting quietly at its foundations. That is perhaps the most reassuring thing about quantum mechanics. It does not need to be understood to work, and neither, tonight, do you. And there is a particular kind of comfort in thinking that the world is precisely defined, that every object has an exact position, that every moving thing has an exact speed, that if you could measure carefully enough, with instruments sensitive enough, you could know everything there is to know about any given particle at any given moment. This is the picture most of us carry without ever examining it, the assumption that reality is crisp and sharp underneath, even when our measurements are rough, that the universe knows exactly where everything is, even if we do not. One of the most profound results of quantum mechanics is the quiet dismantling of that assumption, not because our instruments are imperfect, not because measurement is difficult, but because the universe itself, at its smallest scales, is fundamentally and irreducibly imprecise. Not sharp underneath with blurry measurement on top, but genuinely, inherently, built from a kind of irreducible fuzziness that no instrument, however perfect, could ever see through. This is what Werner Heisenberg showed in 1927, and the principle that bears his name is one of the most important and most misunderstood results in all of physics. Werner Heisenberg was 25 years old when he first grasped the core of it. He was working in Copenhagen, collaborating with Niels Bohr, turning over the deepest puzzles of the new quantum theory. He was thinking about what it actually means to measure something, not in the abstract but concretely, physically. What does measurement require, and what does it inevitably disturb? Start with a simple image. Suppose you want to find the position of a very small particle, an electron, say. To see something, you need light to bounce off it and reach your eyes, or your detector. Without light touching the object, you cannot observe it. But light comes in photons, and photons carry energy. When a photon bounces off an electron to tell you where the electron is, the photon kicks the electron. It gives it a push. It changes the electron's speed and direction. So in the very act of finding out where the electron is, you have disturbed how it is moving. You gained information about its position, you lost precision about its momentum. You might think, use gentler light, lower energy photons, a softer touch, less disturbance to the electron's motion. But here is the problem. Lower energy photons have lower frequency, which means longer wavelength, and a wave cannot pinpoint a location more precisely than its own wavelength allows. A long wavelength gives you a blurry position reading. To get a precise position, you need short wavelength light. But short wavelength light carries high energy photons that kick the electron hard and destroy your knowledge of its momentum. There is no way to win. Precision in one direction costs you precision in the other. Use gentle light, and you know the momentum well, but the position is vague. Use sharp light, and the position is crisp, but the momentum is scrambled. This was Heisenberg's first way of seeing it, a practical argument about measurement and disturbance. But he went deeper than that, much deeper, because he realized that this trade-off was not just a consequence of the clumsiness of photons. It was not just a practical limitation waiting to be engineered around. It was a mathematical consequence of the wave nature of quantum particles themselves. The uncertainty is not in the measurement, it is in the particle. Here is what that means. Position and momentum, where a particle is and how it is moving, are not two separate, independent properties that the particle possesses simultaneously and fully. They are what physicists call conjugate variables. They are linked together in the mathematics of quantum mechanics in a way that makes it impossible for both to be precisely defined at the same time. Not impractical, not difficult, impossible. The more sharply defined a particle's position is, the more precisely it is located in space, the more completely undefined its momentum becomes, and the more precisely its momentum is defined, the more exactly you know how it is moving, the more completely its position smears out across space. This is not a statement about what we can know, it is a statement about what exists. The particle does not have a precise position and a precise momentum simultaneously. It cannot. The universe does not permit it. Heisenberg expressed this in a mathematical relationship. The product of the uncertainty in position and the uncertainty in momentum can never be smaller than a certain tiny fixed value, a value set by Planck's constant, that small fundamental number we encountered when Planck first proposed the quantum. This means the trade-off is exact and absolute. There is a hard mathematical floor on how much can be known simultaneously, a minimum combined uncertainty that cannot be reduced, no matter how perfect the instruments, no matter how careful the experiment, no matter how many times you try. Planck's constant is extraordinarily small, which is why we do not notice this fuzziness in everyday life. For a thrown ball, the uncertainty that Heisenberg's principle demands is so laughably tiny compared to the size of the ball and the speed of its motion that it has no practical consequence whatsoever. The ball has, for all purposes that matter at human scales, a perfectly definite position and a perfectly definite speed at every moment. The fuzziness is there, mathematically, but it is buried so deep beneath the scale of anything we can measure that it is invisible. It only becomes significant, only becomes the dominant feature of reality when you zoom in to the scale of electrons and atoms. There, Planck's constant is not negligible. There, the uncertainty is not a rounding error. There, it is the main event. The uncertainty principle is not limited to position and momentum. It applies to other pairs of conjugate variables as well. And one of those pairs has consequences so beautiful and strange that it deserves a moment of its own. The other pair is energy and time. The uncertainty in the energy of a quantum system and the uncertainty in when that energy is defined are linked in the same way as position and momentum. A system measured over a very long time can have a very precisely defined energy, but a system that exists for only a very short time necessarily has a large uncertainty in its energy. This means that for very short intervals of time, and in the quantum world, very short can mean almost inconceivably brief, the energy of a region of space can fluctuate wildly. Uncertainty in energy over a short enough time means that energy can, in effect, appear from nowhere, as long as it disappears again quickly enough. The universe, at these scales, allows a kind of temporary borrowing, a brief, spontaneous fluctuation in energy that would be forbidden over any longer period. And this borrowing has real, measurable consequences. Empty space is not truly empty. What we call a vacuum, a region with nothing in it, is, at the quantum level, seething, constantly fluctuating, constantly producing pairs of particles that pop into existence from nowhere, exist for an instant too brief to measure directly, and then annihilate each other and disappear again. These are called virtual particles. They are not metaphors. They have measurable effects on real experiments. The force between certain metal plates placed very close together in a vacuum, called the Casimir effect, is partly a consequence of these fluctuations. Empty space hums. The vacuum is alive with temporary things. And this is a direct consequence of Heisenberg's uncertainty principle, applied to energy and time. Take a moment with that image. The air in the room around you, if you could remove every atom from it, would still not be nothing. It would be a quantum vacuum, seething with fluctuations, with virtual particles appearing and vanishing on timescales too short to observe directly. Nothingness, at the quantum level, is not available. The universe will not sit still long enough to be empty. There is a philosophical dimension to the uncertainty principle that physicists have debated since Heisenberg first wrote it down. What does it mean for reality to be fundamentally imprecise? What does it mean that the universe does not keep exact records of where its particles are and how they are moving? Is this a limitation of reality itself, or a sign that our concept of a particle with a definite position and momentum is simply the wrong way to think about what an electron actually is? Heisenberg himself leaned toward the view that the uncertainty was fundamental, that asking for the precise position and momentum of an electron simultaneously was like asking for the precise color and location of a musical note, a question that sounds meaningful but is actually asking for something that does not exist. Others were less comfortable with this. Einstein, again, found it deeply troubling. He spent years trying to construct thought experiments that would defeat the uncertainty principle, scenarios where you could measure both position and momentum precisely, circumventing Heisenberg's limit. Bohr, each time, found the flaw in the argument. The principle held. It always held. And Einstein, though he never fully made peace with it, could not break it. The universe keeps its own uncertainty. It does not owe us crisp, complete knowledge of its inner workings. At the smallest scales, it maintains a kind of deliberate vagueness, a softness at the edges of things, a refusal to be pinned down completely. Position blurs into momentum, energy flickers across time, the vacuum hums with temporary particles that no one ever quite catches in the act of existing. And all of this, the uncertainty, the fuzziness, the constant flickering of the vacuum, is not a flaw in the universe. It is a feature, a deep structural property of reality at the level where reality is most itself, where it has not yet been averaged out into the smooth, solid-seeming world of tables and chairs and sleeping bodies. You are made of particles that no one, not you, not a physicist, not any instrument ever built, can pin down completely. Every electron in every atom of your body is slightly, irreducibly uncertain in its position, uncertain in its momentum, existing in that quantum fuzziness that Heisenberg first described on a winter night in Copenhagen almost 100 years ago. And the universe is holding all of that uncertainty together, right now, into something coherent and warm and breathing. That is not a troubling thought. It is, in its own quiet way, a rather beautiful one. The fuzziness at the bottom of things is not chaos. It is the texture of reality itself, and you are resting inside it. Every particle in the universe carries something with it. Not a label, not a fixed set of properties written down somewhere in advance. Something more like a cloud of possibilities, A spread of potential outcomes, each one weighted, each one real in its own way, waiting for the moment when the universe asks a question, and one of them must become the answer. Physicists have a name for this cloud. They call it the wave function. And it is, in some sense, the most important idea in all of quantum mechanics. Not because it is the most dramatic, but because it is the most complete. The wave function is the fullest description of a quantum particle that physics has. It contains everything that can be known, everything that is, in any meaningful sense, there. Tonight we are going to sit with what the wave function is, not the mathematics of it. The mathematics is beautiful, but not what we need in the dark and the quiet. Just the idea, the shape of it. The strange and somehow tender picture it paints of what a particle actually is when nobody is looking at it. Start with the word wave. When you hear that word, you probably picture something physical. Water rising and falling, sound moving through air, light rippling outward from a source. These are real waves, disturbances in real physical stuff, moving through real space, carrying energy from one place to another. The wave function is not quite like any of these. It is not a wave in a physical medium. It does not ripple through water or air or any material thing. It is a wave of probability, a mathematical object that spreads out through space, and whose height at any given point tells you how likely the particle is to be found there if you were to look. Where the wave function is tall, the particle is likely. Where it is small, the particle is unlikely. Where it is zero, the particle will not be found at all. Think of it as something like a map of potential. Not a map of where the particle is, but a map of where it might be, and how strongly each possibility is weighted. A landscape of probability, spread out across space, shifting and evolving over time according to precise mathematical rules. The particle is not at any one point on this map. It is, in a genuine sense, spread across all of it, present everywhere the wave function has any value, absent only where the wave function is zero. It is not hiding at one location while we fail to find it. It is genuinely distributed across the whole landscape of possibility. This is one of those ideas that sounds like it should be a metaphor, like we are saying the particle behaves as if it were spread out, while really it is secretly somewhere definite. But that is not what quantum mechanics says. The spreading is real. The distribution is real. The particle, before measurement, genuinely has no single location. The wave function is not a description of our ignorance. It is a description of the particle itself. Now think about what happens over time. The wave function does not sit still. It evolves. It moves and spreads and changes shape according to an equation that Erwin Schrödinger wrote down in 1926. The Schrödinger equation is one of the central equations of physics, perhaps the most important equation of the 20th century, alongside Einstein's field equations of general relativity. It is a wave equation. It describes precisely how the wave function of any quantum system changes from one moment to the next, given what forces and fields the particle is experiencing. The equation is deterministic. Given the wave function at one moment, it predicts the wave function at any future moment with perfect precision, which means the evolution of possibilities is perfectly determined. It is only the outcome of any particular measurement that is not. The cloud of probability evolves smoothly and predictably, but which possibility the universe selects when a measurement finally happens is irreducibly random. Both things are true at once. Perfect determinism in the evolution of possibilities, perfect randomness in the selection of outcomes. The wave function moves like clockwork. The measurement result lands like a throw of dice. This is another of the deep strangeness of quantum mechanics that takes time to absorb. We are used to a world where randomness means we do not know enough, where if you could track every detail, every cause, every initial condition, you could in principle predict every outcome. Quantum randomness is different. It is not ignorance dressed up as uncertainty. It is genuine, fundamental, irreducible randomness built into the structure of the universe. Even a perfect knowledge of the wave function, even holding in your mind the complete mathematical description of a particle's state, does not tell you what a measurement will find. It tells you only the probabilities, and beyond those probabilities, there is nothing more to know. Einstein found this intolerable. He said, famously, that God does not play dice. He meant that the universe, at its deepest level, must be deterministic, that the randomness of quantum mechanics must be a sign of incompleteness, not a fundamental feature of reality. That behind the wave function, behind the probabilities, there must be hidden variables, deeper facts about the particle's state that we simply have not found yet, which would restore determinism if only we could uncover them. This argument occupied him for the last 30 years of his life. And as we touched on before, experiments eventually showed, conclusively, mathematically, beyond reasonable dispute, that no such hidden variables exist. The randomness is real. God, whatever that word means in this context, does play dice. Or perhaps, more precisely, the universe does not decide until it must, and when it does, it decides in a way that nothing and no one could have predicted in advance. Now comes the moment that sits at the very heart of quantum mechanics. The moment that no interpretation has fully explained, that no physicist has fully resolved, that remains, after a century of thought, genuinely open. The moment of measurement. Before measurement, the wave function spreads across space, encoding all possibilities. After measurement, there is one outcome, one definite result. The particle is found here, not there. Spin up, not down. This energy, not that one. Something has happened between the before and the after. The spread of possibilities has given way to a single fact. Physicists call this wave function collapse. The wave function, which had been distributed across many possibilities, collapses instantly to a single point, the point where the particle was found. All the other possibilities vanish. What was a cloud of weighted outcomes becomes a single, definite answer. The question that nobody has satisfactorily answered is, what causes the collapse? What is it about measurement that singles out one possibility and eliminates all the others? What counts as a measurement? Does it have to involve a conscious observer? Does it happen whenever a quantum particle interacts with any large system? Is the collapse even real? Or is it an illusion created by the way we experience a universe that is actually branching into all outcomes simultaneously? These questions have names and elaborate frameworks built around them: the Copenhagen interpretation, the many worlds interpretation, decoherence theory, relational quantum mechanics, and none of them has won the argument. The collapse remains mysterious. The transition from many to one remains unexplained at the deepest level. And yet the mathematics works. This is worth pausing on. The Schrödinger equation describes the wave function's evolution with extraordinary precision. The probability rules derived from it match experiment after experiment to more decimal places than any other theory in the history of science. Quantum mechanics is the most accurately tested theory ever produced by human beings. Its predictions have been confirmed to a degree of precision that strains the imagination. And yet the interpretation, the question of what it all actually means, what is physically happening, what the wave function really is, remains unsettled. We have a perfect map. We do not agree on what the territory is. There is a beautiful image that comes from thinking about the wave function carefully. Every particle you have ever touched was once a spread-out cloud of probabilities. The electrons in the atoms of the pillow beneath your head, the atoms of your own hand, were at some earlier moment distributed across a landscape of possibility, not yet localized, not yet definite. They became definite through interaction, through measurement, through contact, through the constant process by which the quantum world decoheres into the everyday world of fixed, solid-seeming things. The solidity around you is the accumulated result of countless wave function collapses, countless resolutions of possibility into fact, stretching back through time. Every object you have ever encountered arrived at its definiteness through this process. Every surface, every texture, every fixed and familiar thing in your life is, at the quantum level, the settled outcome of what was once a cloud of open possibilities. The world you live in is made of answers, but underneath every answer, there was once a question. A wave function, spread out and waiting, holding every possibility gently, until the universe asked, and something became real. That process is still happening, right now, in every atom around you and inside you. Wave functions evolving, interacting, collapsing into outcomes, decohering into the stable world of everyday experience. The hum of quantum possibility resolving, moment by moment, into the quiet and solid world in which you are lying. All of it managed by an equation written down 100 years ago, by a man in Zurich who was not entirely sure what his own equation was describing. Schrödinger gave us the mathematics. The meaning is still arriving. Slowly, carefully, the way all the deepest meanings do. And tonight, that is exactly the right pace. Slow, unhurried, one possibility at a time, settling gently into place. The wave function of this moment, collapsing softly into sleep. Somewhere in the history of physics, there is a letter, written by Albert Einstein, to a colleague, in which he used a German phrase that translates roughly as spooky action at a distance. He meant it as a criticism, as a way of pointing to something he found deeply wrong with quantum mechanics, something that seemed to him not mysterious and beautiful but simply impossible, a feature of the theory that suggested, if you took it seriously, that two particles on opposite sides of the universe could be instantly connected, that what happened to one could immediately affect the other, with no signal passing between them, no time for any influence to travel, no mechanism of any kind that physics could account for. Einstein thought this was absurd. He thought it proved quantum mechanics was incomplete. He was wrong. The spooky action is real, and it is one of the most quietly extraordinary things in all of science. The phenomenon is called quantum entanglement. And to understand what it is, we need to start with the wave function idea we sat with in the last section. Remember that a quantum particle, before measurement, exists in a superposition of possible states. Its properties are not fixed. They are held open, distributed across possibilities, described by a wave function that encodes all outcomes and their probabilities. Now imagine two particles that interact with each other, collide, or are created together from a single source, or pass through the same interaction. Something happens between them that links their wave functions together. Instead of each particle having its own separate wave function describing its own separate possibilities, the two particles share a single combined wave function. Their states become correlated at the deepest level, woven together, described jointly rather than individually. This is entanglement. Two particles whose quantum states cannot be described independently of each other, no matter how far apart they travel. Here is what that means in practice. Take two electrons and prepare them in an entangled state where their spins are opposite. If one is up, the other must be down, but neither has a definite spin yet. Both are in superposition. Now send them in opposite directions. Let them travel as far as you like, across a room, across a city, across the galaxy if you had the patience. The entanglement does not weaken with distance. It does not fade as the particles separate. It persists, intact, no matter how far apart the particles move. They remain connected through their shared wave function, which does not belong to either particle alone, but to both of them together. Now measure the spin of one particle. Suppose you find it is spin up. At that moment, instantly, not after a brief delay, not after some signal has had time to travel, the other particle's spin becomes definite. It is spin down. Not probably spin down. Not spin down a moment later when the information arrives. Spin down now, at the instant you measured its partner, regardless of how far away it is. The measurement of one particle collapses the shared wave function. Both particles become definite simultaneously, across any distance, with no time for anything to pass between them. This is what Einstein called spooky. And his instinct was, in one sense, completely understandable. Physics had built itself on the principle of locality, the idea that things can only be directly influenced by their immediate surroundings, and that any influence traveling from one place to another must take time, traveling at most at the speed of light. Einstein's own theory of relativity was built on this principle. Nothing travels faster than light. No influence, no signal, no cause can outrun light. And here was quantum mechanics apparently violating this, apparently allowing an instantaneous connection across any distance whatsoever. Einstein believed that this proved quantum mechanics was missing something. He argued, with two colleagues named Podolsky and Rosen, in a famous 1935 paper, that the only sensible explanation was that the particles must already have had definite spins before the measurement. That they were like a pair of gloves separated into two boxes. Open one box and find a left glove, you instantly know the other box contains the right glove, but no spooky action was involved. No instant influence crossed the space between them. The gloves always were what they were. You just did not know yet. Einstein believed the same must be true of entangled particles. They must carry hidden definite properties from the moment of their creation. The apparent randomness, the apparent non-locality, must be a consequence of our ignorance of these hidden properties. This was a clean and reasonable argument. It was also, as it turned out, wrong. In 1964, a physicist named John Bell did something remarkable. He took the question of whether quantum mechanics was complete, whether hidden variables could explain the correlations between entangled particles, and turned it into a mathematical test. He derived a set of inequalities, relationships between measurable quantities, that any theory based on hidden variables would have to satisfy. If the particles were like gloves, secretly carrying their properties from the start, Bell's inequalities would hold. If quantum mechanics was right, and the properties were genuinely undecided until measurement, Bell's inequalities would be violated. He had found a way to ask the universe which one was true. Through the 1970s and 80s, experimenters led by a French physicist named Alain Aspect and others built increasingly sophisticated experiments to test Bell's inequalities with entangled particles. The results came back clearly, unmistakably, consistently. Bell's inequalities were violated. The particles were not carrying hidden definite properties. The correlations between them were stronger than any hidden variable theory could produce. Quantum mechanics was right. The entanglement was real. The spooky action was real. The universe is non-local at the quantum level, in a way that Einstein spent the last decades of his life refusing to accept, and that experiments have now confirmed beyond any serious doubt. Alain Aspect, along with John Clauser and Anton Zeilinger, received the Nobel Prize in Physics in 2022 for this work. 100 years after the quantum revolution began, the world finally gave its formal recognition to the experiments that proved the universe is stranger than Einstein was willing to allow. Now, there is something important to be said here, because entanglement is often described in ways that make it sound as though it allows faster-than-light communication. It does not. And understanding why not is itself a beautiful piece of quantum reasoning. When you measure your entangled particle and find it is spin up, you instantly know your partner particle is spin down. But the result you got, spin up, was random. You could not control it. You could not choose to get spin up in order to send a message. The outcome is determined by the universe, not by you. And your partner, receiving their particle and measuring it, gets a random result too. Only when you and your partner later compare notes, through an ordinary, light-speed limited communication channel, do you discover that your results were correlated. The correlation is instantaneous. The knowledge of the correlation is not. No information travels faster than light. No message can be encoded in the entanglement. The non-locality is real, but it cannot be used as a telephone. What it can be used for is something subtler, and in some ways more interesting. Quantum cryptography uses entanglement to create communication channels whose security is guaranteed by the laws of physics rather than by the difficulty of mathematical problems. Any attempt to eavesdrop on an entangled communication channel disturbs the entanglement in a way that is detectable. The physics itself prevents undetected interception. Quantum computing uses entanglement to link qubits together in ways that allow calculations impossible for any classical machine. Quantum teleportation, which is real though it does not work the way science fiction imagines, uses entanglement to transfer the complete quantum state of a particle from one location to another, without the particle itself traveling. The strangeness is being put to work. The spooky action is becoming technology. But set aside the applications for a moment. Just sit with the phenomenon itself. Two particles, created together, sharing a wave function sent off in opposite directions across whatever distance you choose. Still connected, still described by a single mathematical object that does not belong to either of them alone. Still, in some sense that physicists have measured and confirmed and cannot fully explain, aware of each other. When you measure one and find it spin up, and its partner across the galaxy instantly becomes spin down, nothing traveled between them, no signal, no wave, no particle carrying the news. The connection was always there. It was never broken by the distance. Distance, which seems so fundamental to the everyday world, so obviously important, so clearly the reason things are separate from each other. Distance simply does not sever entanglement. The shared wave function does not care how far apart the particles are. Space, at the quantum level, does not isolate things the way it seems to at the level we live at. There is something in this that feels almost like a story about belonging, about the way things that were once connected carry that connection forward, across any distance, in a way that nothing can erase. Two particles that shared a moment, a source, an interaction, continuing to be described together, continuing to be correlated, long after the world has separated them, the universe keeping a record of what was once close. Whether that image means anything beyond its own beauty is not a question for physics. Physics deals in measurements and mathematics, and the careful, patient testing of predictions against reality. But the image is real, the entanglement is real, the correlation across distance is real, and there is no reason not to find it beautiful as well as true. Right now, in laboratories around the world, pairs of entangled photons are being created and separated and measured. Their correlations are being confirmed, again and again, to extraordinary precision. And every confirmation is another quiet affirmation of something the universe has apparently always known. That separation is not the same as disconnection. That distance does not dissolve what was once woven together. That some connections once made persist in a way that space alone cannot undo. Let that thought settle wherever it lands. In the physics, in the image, in whatever corner of the mind finds it restful or remarkable or simply interesting in the dark. The particles do not mind being strange. They have been this way since long before anyone noticed, and they will continue, quietly entangled, long after tonight. There is a rule in the everyday world that feels so obvious it barely seems worth stating. If you do not have enough energy to get over something, you do not get over it. A ball rolled gently toward a hill will slow down, stop partway up, and roll back. It does not have enough energy to reach the top, so it stays on the side it started on. A car without enough fuel will not make it to the next town. A person without enough strength cannot lift a weight beyond their limit. Energy is the currency of motion, and if you cannot pay the cost, you do not cross. This feels like one of the most solid, unbreakable rules of the physical world. Not a convention or an approximation, but something close to a logical necessity. You cannot be somewhere you do not have the energy to reach. Quantum mechanics disagrees. At the scale of particles, this rule does not hold. A particle can cross a barrier it does not have enough energy to cross. It can appear on the other side of a wall without ever having had enough energy to climb over it. Not sometimes, under special conditions, in exotic laboratory setups. Constantly, everywhere. Right now, inside your body, inside every piece of metal and semiconductor around you, inside every star in the sky. Particles are crossing barriers they have no classical right to cross. Walking through walls, in a precise and literal quantum sense. This is called quantum tunneling, and it is one of the most consequential phenomena in the universe. To understand how it works, we need to return to the wave function. Remember that a quantum particle is not a tiny solid ball sitting at a definite point in space. It is a wave function, a spread of probability, a cloud of possibility, distributed across space according to precise mathematical rules. Now, what happens when that wave function meets a barrier? A region of space where the particle, classically, should not be able to go. A wall of energy it does not have enough to climb. In the classical picture, the answer is simple. The particle hits the barrier, cannot cross, bounces back. End of story. But the wave function does not bounce back cleanly. It penetrates. When a quantum wave function encounters a barrier, it does not simply stop at the edge. It extends into the barrier. It reaches through. The probability of finding the particle decreases as it goes deeper into the barrier, exponentially, like a sound fading as it passes through a thick wall, but it does not reach zero immediately. It tails off gradually, and if the barrier is thin enough, there is still a small but real probability of finding the particle on the other side. The wave function leaks through, and if the wave function has any value on the other side of the barrier, there is a genuine probability that a measurement would find the particle there. Which means the particle can get there, not by going over the barrier, not by somehow acquiring the energy to climb it, but by tunneling through it, by existing, with some probability, in a place the classical rules say it cannot reach. The thinner the barrier, the more the wave function leaks through, and the higher the probability of tunneling. The thicker the barrier, the more the wave function is suppressed, and the lower the probability. For everyday objects, for a ball, for a person, for anything made of vast numbers of atoms, the probability of tunneling through any macroscopic barrier is so unimaginably small that it never happens in any practical sense. You will not walk through a wall. The quantum tunneling probability for a human body passing through a solid door is a number so close to zero that writing it out would require more zeros after the decimal point than there are atoms in the observable universe. It is not forbidden. It is just so improbable that it has never happened and never will in any time frame that has meaning. But for particles, for electrons, for protons, for the light, fast, quantum things that make up the world at its smallest scale, tunneling is not a rare, exotic event. It is a routine part of how the universe operates. The most extraordinary example of quantum tunneling, and the one that affects your life most directly, happens 93 million miles away, in the core of the sun. The sun shines because of nuclear fusion, because hydrogen nuclei, protons, are being pushed together under the enormous pressure and temperature at the sun's core until they fuse into helium, releasing vast amounts of energy in the process. This is the fire that has warmed the Earth for 4.5 billion years, the source of almost all the energy in every ecosystem that has ever existed, the light that makes life possible. And it should not be happening. Here is the problem. Protons are positively charged. Positive charges repel each other. The electromagnetic force pushes them apart, harder and harder the closer they get. To fuse, two protons must get close enough for a different force, the strong nuclear force, to grab them and hold them together. But to get that close, they must first overcome the electromagnetic repulsion. And calculations show that the protons in the sun's core, even at the extraordinary temperatures found there, do not actually have enough energy to overcome that repulsion. The barrier is too high. The protons are moving too slowly. By classical physics, they should not be able to get close enough to fuse. The sun should not be able to shine, and yet it does, because the protons do not go over the barrier, they tunnel through it. Each individual tunneling event has a very low probability, but the sun's core contains an almost incomprehensible number of protons, and they are colliding constantly, and even a tiny probability multiplied by an enormous number of attempts produces a steady, reliable rate of fusion. Enough to have kept the sun burning for billions of years. Enough to warm this planet through every season of every year since before life existed here. The warmth you feel from sunlight is the accumulated result of quantum tunneling events happening in a distant star. The light that grew every plant that ever lived, that powers every ecosystem, that makes the sky blue in the daytime, all of it tunneled into existence. Tunneling is not only in the stars, it is in the devices you use every single day. The flash memory in computers and phones, the storage that holds everything from photographs to music to the contents of entire hard drives, works by exploiting quantum tunneling. Electrons tunnel through thin insulating barriers to store and retrieve data. The reading and writing of information in these devices is a quantum mechanical process. Every file you have ever saved, every photograph you have ever taken, every message stored on a device, held in place by the careful management of quantum tunneling. The tunnel diode, used in electronics since the 1950s, operates on tunneling. The scanning tunneling microscope, one of the most extraordinary instruments ever built, capable of imaging individual atoms, works by measuring the tiny tunneling current that flows between a sharp metal tip and a surface when they are brought close enough together. The tunneling current is exquisitely sensitive to the distance between the tip and the surface. Change that distance by the width of a single atom, and the current changes dramatically. This sensitivity is what allows the microscope to feel its way across a surface and map individual atoms. An instrument that sees atoms by measuring particles leaking through the space between them. And then there is something closer still. Something happening not in the sun and not in your devices, but in you. Inside the cells of your body, inside the long, twisted molecules of DNA that carry the instructions for everything you are, quantum tunneling plays a role. The DNA double helix is held together partly by hydrogen bonds, connections between the two strands that keep the molecule stable and allow it to be read and copied. These hydrogen bonds involve protons sitting in specific positions, and occasionally a proton will tunnel from one position to another within the bond. When this happens at the wrong moment, during the copying of DNA, it can result in a mutation, a change in the genetic code. Quantum tunneling may be one of the sources of the genetic mutations that drive evolution. The random, unpredictable quantum leaping of protons through energy barriers, happening in the molecules that carry the instructions for life, introducing the variations that natural selection works with. Evolution, written in quantum uncertainty. Take a moment with that. The process that produced every species that has ever lived on this planet, including the species lying here in the dark, listening to these words, may owe something to quantum tunneling. To the wave function of a proton, extending through a barrier it had no classical right to cross, arriving on the other side and changing a molecule, and eventually, through an enormously long chain of consequences, changing the history of life. The quantum world is not separate from the world you live in. It is not a strange realm that only exists in physics laboratories and textbooks. It is underneath everything. The sun tunnels, your cells tunnel, your devices tunnel. The stars that formed the atoms in your body began their burning through tunneling. The universe uses quantum mechanics not as an exotic exception, but as a basic, routine, indispensable tool. Right now, as you lie still in the dark, in every cell of your body, in every atom of the air around you, quantum tunneling is happening. Particles crossing barriers they should not be able to cross. Wave functions leaking through walls. The universe quietly doing what classical physics said was impossible, doing it constantly, doing it without effort, the way it has always done. Not as something remarkable, as ordinary business. The walls of the world are thinner than they appear. At the deepest level, they always have been. and the particles have always known it. We began this journey with the atom. In those early sections, we found it hollowed out, mostly empty space, a tiny dense nucleus at the center, electrons somewhere in the surrounding void. We found that the planetary model, the picture of electrons orbiting like tiny moons, could not be right, because a charged particle in orbit should radiate energy and spiral inward, and atoms do not do that. Atoms are stable, and something had to explain why. We left that question open, as a thread to be picked up later. Later is now. We have spent the sections since then building the tools we need: wave functions, superposition, quantization, the uncertainty principle. All of that was not a detour. It was preparation. Because the answer to why atoms are stable, why electrons do not spiral into the nucleus, why matter holds together, why you exist, is a quantum answer. And now we have enough of the language of quantum mechanics to hear it properly. The key insight came from a young Danish physicist named Niels Bohr in 1913. Bohr took Planck's idea of quantization and applied it directly to the atom. He proposed that electrons in an atom do not orbit the nucleus in any path they choose, the way a planet can orbit at any distance from the sun. Instead, electrons can only exist at certain specific distances from the nucleus, certain allowed orbits, and nothing in between. Like the stairs we imagined when we first talked about quantization, the electron can be on the first step, or the second step, or the third, but not floating between steps, never between steps. These allowed orbits correspond to specific, fixed amounts of energy, and this is why they are called energy levels, not orbits exactly, though that word is still used loosely. Energy levels. Fixed rungs on a quantum ladder. An electron in an atom sits on one of these rungs. It stays there, stable, not radiating energy, not spiraling inward, simply existing at that energy level in the way a ball rests at the bottom of a bowl. The lowest rung, the ground state, is where the electron would rather be. It is the state of lowest energy, the most stable, the quietest. The electron does not fall any further than the ground state because there is no further to fall. The ground state is the floor. This is why atoms do not collapse. The electron cannot spiral inward forever because the inward journey stops at the lowest allowed energy level. Quantum mechanics protects the atom. The quantization of energy is the reason matter is stable, the reason you are here. But electrons do not always stay in the ground state. They can be excited. If a photon, a particle of light carrying exactly the right amount of energy, comes along and is absorbed by the atom, the electron can use that energy to jump to a higher rung. Not any higher rung. The specific rung that corresponds exactly to the energy of the photon. Too little energy and the photon is ignored. The electron has no rung it can reach with that amount, so the photon passes through. Too much energy and again, no match. The photon is not absorbed. Only exactly the right energy produces absorption. Only a photon whose energy corresponds precisely to the gap between two allowed levels will be taken in. This is called excitation. The electron absorbs the photon and jumps to a higher energy level, a higher rung on the quantum ladder. But it does not stay there. Higher energy states are unstable. The electron wants to return to its lower, quieter state. And so, after a very brief time, sometimes almost instantly, sometimes after a tiny delay, it falls back down. And when it falls, it releases a photon. A photon carrying exactly the same amount of energy as the gap it just crossed. The same energy it absorbed on the way up, now released on the way down. Energy in, energy out, in precise and exact packages. Nothing lost, nothing gained, everything accounted for. This released photon has a specific energy, and energy determines frequency, and frequency determines color, which means the photon released has a specific color. A color that corresponds exactly to the energy gap between two specific levels in that atom. And since every element has its own unique set of energy levels, its own unique arrangement of rungs on its quantum ladder, every element releases its own unique set of colors when its electrons fall back down. A fingerprint made of light. This is why neon signs glow the colors they glow. Electricity passes through the neon gas, exciting the electrons in the neon atoms to higher energy levels. The electrons fall back, releasing photons. And neon's particular set of energy levels produces photons in the red and orange part of the spectrum. Not of element, red because the gaps between neon's specific energy levels correspond to exactly those frequencies of light, and no others. Change the gas and you change the colors. Argon glows lavender, krypton glows pale green, mercury vapor glows blue-white, each one broadcasting its own quantum signature in light, each one showing you, if you know how to read it, the precise ladder of energy levels inside its atoms. And this is not only true of glowing signs in city streets at night. It is true of everything that emits or absorbs light. Every source of light, every colored surface, every glowing gas anywhere in the universe is doing something related to this same process. Electrons moving between energy levels, photons being absorbed or emitted, the quantum ladder of each element being climbed and descended, over and over, releasing and absorbing light in precise and characteristic amounts, which brings us to something that deserves a long, quiet moment of appreciation. Something that is, in a certain light, one of the most remarkable things human beings have ever worked out. We can read the chemistry of stars. A star is an almost incomprehensibly distant object. The nearest star beyond our own sun is so far away that light, traveling at the fastest speed anything in the universe can travel, takes more than 4 years to reach us from it. Most of the stars you can see on a clear night are hundreds or thousands of light years away. No human being has ever gone near one, no probe has ever visited one, no sample has ever been collected from one. And yet we know, with great confidence, what they are made of. Here is how. When light from a star reaches us, we can spread it out into its component colors using a prism or a diffraction grating, the same principle as a rainbow, which spreads sunlight into its spectrum. And when we look carefully at the spread-out spectrum of starlight, we find dark lines, specific frequencies where light is missing, gaps in the rainbow. These dark lines appear because as light travels outward through the outer layers of a star, atoms in those layers absorb photons of exactly the frequencies that correspond to their energy level gaps. The absorbed photons are missing from the light that reaches us. And the pattern of missing frequencies is unique to each element. So by reading the dark lines in starlight, comparing their positions to the known energy level signatures of every element, we can tell exactly which elements are present in the star's outer atmosphere. Hydrogen, helium, carbon, oxygen, iron, calcium, all readable in the light, all identified by their quantum fingerprints, each element announcing itself through the precise gaps in its quantum ladder, printed into the light that has traveled for years or centuries or millennia to reach the instrument that reads it. We have mapped the chemistry of stars billions of light years away. We have found the same elements everywhere we look. Hydrogen most abundant, then helium, then the heavier elements in their various proportions. The universe, it turns out, is made of the same stuff everywhere, the same elements, following the same quantum rules, their electrons climbing and falling the same ladders of energy, from the nearest star to the most distant galaxy we can observe. Quantum mechanics is not a local rule, it is the law everywhere. Now let us go one level deeper into the atom, because the energy levels of electrons do more than produce colored light. They determine everything about chemistry. Every reaction that has ever happened, every bond that has ever formed, every molecule that has ever existed, all of it is a consequence of how electrons arrange themselves in atoms and how those arrangements interact with each other. Electrons in atoms fill their energy levels in a very specific order. Not randomly, not all piling into the lowest level together, but following precise quantum rules about how many electrons can occupy each level and in what configurations. One of these rules is called the Pauli exclusion principle, named for the Austrian physicist Wolfgang Pauli, who proposed it in 1925. It states that no two electrons in the same atom can be in exactly the same quantum state simultaneously. Each electron must differ from every other in at least one quantum property. This sounds like a technical constraint, but its consequences are vast. Because of the Pauli exclusion principle, electrons cannot all crowd into the lowest energy level. Each level has a limited number of spaces, and once those spaces are filled, the next electrons must go to higher levels. The result is a layered structure, electrons filling the available levels from the lowest upward, building up in a specific pattern that depends on how many electrons the atom has. This pattern, the configuration of electrons in their levels, is different for every element, and it determines almost everything about how that element behaves, how readily it bonds with other atoms, what kinds of bonds it forms, how many partners it can bond with, whether it is chemically reactive or inert, whether it is a metal or a non-metal, whether it conducts electricity or insulates against it. The periodic table of elements, that familiar grid of boxes that appears on the walls of chemistry classrooms everywhere, is, at its deepest level, a map of quantum electron configurations. The reason elements in the same column of the periodic table share similar chemical properties is that they have similar arrangements of electrons in their outermost levels. The outermost electrons are the ones that interact with other atoms, that form bonds, that participate in reactions, and elements with the same outer configuration behave similarly because their outermost quantum ladders look the same. Sodium and potassium are both soft, reactive metals that behave in strikingly similar ways. Both react vigorously with water, both form similar compounds, both share many properties, because both have a single electron in their outermost level, sitting alone on the top rung, ready to be given away. Helium and neon and argon are all chemically inert, almost completely unwilling to bond with anything, because their outermost levels are completely full, leaving no spaces for interaction, no loose electrons, no available gaps. A full outer level is a closed, satisfied, unreactive configuration. An incomplete outer level is an invitation to bond. Chemistry is quantum mechanics, playing out slowly enough for us to observe. Every reaction in a beaker, every burning log, every rusting nail, every breath drawn into your lungs, and every exchange of oxygen and carbon dioxide in your blood, all of it is electrons moving between energy levels, forming and breaking bonds, following the quantum rules that Bohr and Pauli and others worked out a century ago. The chemistry of life is the quantum mechanics of electrons. And now, circle back to where we began tonight, with this section. The question we left open near the start of this journey: why do atoms not collapse? Why do electrons not spiral inward? Why does matter hold together? Has its answer here. Electrons occupy fixed energy levels. The lowest level is the floor. There is nowhere further down to fall. The quantization of energy, which began as a mathematical trick proposed reluctantly by a cautious German physicist trying to fix an equation about glowing metal, turns out to be the reason the world exists in the form it does. Without quantized energy levels, electrons would spiral into nuclei, atoms would collapse, matter would not hold together. The universe would be a featureless fog of collapsed matter, with no chemistry, no structure, no stars, no planets, no life. The stairs instead of the ramp, the fixed levels instead of the continuous slide. That single idea, buried in the mathematics of quantum mechanics, is the reason everything you have ever touched or seen or known is here to be touched and seen and known. Lie with that for a moment in the dark. The atoms in your body hold together because their electrons cannot fall past the lowest rung. The air in your lungs holds its chemistry because of the quantum configurations of its electrons. The warmth of the blanket resting on you is electrons in their energy levels, vibrating, conducting heat, following quantum rules that have been operating since long before anyone understood what they were. All of it quantum, all of it held together by the same principle. The universe counting carefully, permitting only whole numbers of steps, allowing nothing to fall further than the floor it has set. There is a kind of order in that. A deep, quiet, structural order, built into the fabric of things at the level of the very small, holding everything above it steady. Not an imposed order, not something from outside, just the way things are, at the bottom, where the rules run deepest. Where the electrons rest on their levels, and the atoms cohere, and the world holds together in the dark. You have spent this whole journey learning about particles, electrons, photons, quarks, neutrinos. They feel like the building blocks of everything, the smallest pieces of the universe. And they are, in a sense. But modern physics has gone deeper. It has found that particles are not the bottom layer. They are not the final answer. Beneath the particles, there is something else. Something that fills all of space, everywhere, all the time. This is the world of quantum fields. And to understand it is to understand that what you call a particle is really just a ripple on an ocean you cannot see. Think about the ocean for a moment. Imagine you are standing on a shore, looking out at the water. You see waves rolling in, breaking against the sand. Each wave seems like a thing. It has a shape, a size, a direction. You could point to it and say, there is a wave. You could watch it travel across the surface. But the wave is not really separate from the ocean. It is made of the ocean. It is a disturbance in the water. The water was there before the wave, and it will be there after the wave is gone. The wave is just a local movement, a temporary pattern, a ripple that rises and then falls back into the vast body of water that holds it. Quantum field theory says, the universe is like that ocean. There is not a collection of particles sitting in empty space. There are fields. There is a field for every kind of particle that exists. There is an electron field that fills all of space, from the edge of the observable universe to the room where you are lying down right now. You cannot see this field. You cannot touch it. It is invisible and silent, but it is everywhere. And an electron is not a little ball that moves through space. It is a ripple in the electron field. It is a wave of energy that rises up in one place and then travels, and when it passes, the field settles back down. There is also a photon field, and that is the field for light. Every beam of light that has ever shone, every ray of sunshine that has ever touched your skin, every glint of starlight that has ever reached your eye, all of it is a ripple in the photon field. The field is always there, filling the entire universe, but it is calm most of the time. When something disturbs it, a ripple forms, and that ripple is what you call a photon. It travels through space at the speed of light, carrying energy from one place to another, and when it reaches you, the field is disturbed locally where it meets your eye, and that disturbance is what allows you to see. This is the most complete picture of reality that physics has ever produced. Quantum field theory describes everything in the known universe except gravity. It describes the electrons that orbit atoms, the photons that carry light, the quarks that make up protons and neutrons, the gluons that hold those quarks together, the W and Z bosons that carry the weak nuclear force. Every particle in the standard model of particle physics is a ripple in its own corresponding field. There is a field for each one, and the fields interact with each other. When an electron ripple moves through the photon field, it creates a ripple in that field, and that is how light is produced. When two particles collide, it is really two ripples in two fields, meeting and exchanging energy. Now we come to something that might be the most important field of all, at least for explaining why the universe looks the way it does. This is the Higgs field. The Higgs field fills all of space, just like all the other fields, but it is different. It has a property that no other field has. It has a non-zero value everywhere, even in what you would call empty space. That means the Higgs field is never completely calm. It is always there, always present, like a kind of cosmic fog that you cannot see, but that pervades everything. And as other particles move through this field, they interact with it. They are slowed down by it. They are given resistance. That resistance is what you experience as mass. A particle that interacts strongly with the Higgs field moves through it like a person wading through deep water. It feels heavy, it is hard to get moving, and once it is moving, it is hard to stop. A particle that interacts weakly with the Higgs field moves through it like a person walking through thin air. It feels light. It zips along with very little resistance. A photon does not interact with the Higgs field at all, which is why it has no mass and always travels at the speed of light. Electrons interact moderately with the Higgs field, which gives them a small mass. Quarks interact more strongly, which gives protons and neutrons most of their mass. Without the Higgs field, every particle would be massless. They would all travel at the speed of light. Atoms would not form. Stars would not exist. You would not exist. For decades, the Higgs field was a theory. It was a beautiful idea, but no one knew if it was real. Scientists needed to find the ripple in the Higgs field, the particle that would prove the field existed. This particle was called the Higgs boson, and finding it was one of the greatest challenges in the history of science. It required a machine so large, so powerful, so precise, that it took thousands of physicists from all over the world and decades of work to build. That machine is called the Large Hadron Collider, or LHC, and it sits in a circular tunnel 27 kilometers around, buried deep beneath the border between France and Switzerland. Inside that tunnel, particles are accelerated to speeds very close to the speed of light and then smashed into each other. The collisions produce showers of new particles, all of them ripples in their respective fields. The detectors surrounding the collision points are like enormous digital cameras, capturing the tracks and energies of these particles as they fly outward. Among all the noise, among the billions and billions of collisions that happen every second, the scientists were looking for a very specific signal. They were looking for a ripple in the Higgs field, and in 2012, after years of searching, they found it. The Higgs boson was detected. It was a moment of triumph. The last missing piece of the standard model had been found. The field that gives mass to everything had been proven real. This is a good moment to pause and let the scale of that achievement settle. The Higgs boson is not something you can see with your eyes. It is not something you can hold in your hand. It is a ripple in an invisible field that fills the entire universe. And human beings, using our intelligence and our curiosity and our tools, reached out across the emptiness and found it. We confirmed that this field is real. We proved that mass is not just a property that things have, but a consequence of the universe being filled with something we could not see. It is one of the most profound discoveries ever made. Now, let us return to the deeper picture. The fields are the true layer of reality. Particles come and go. They appear and disappear. They are created and destroyed in collisions. But the fields remain. The electron field was there before the first electron existed. It will be there after the last electron is gone. It is timeless in that sense. It is the canvas on which the universe is painted. And the canvas is not empty. It is filled with all these fields, overlapping, interacting, constantly fluctuating. Even in what you would call empty space, the fields are not calm. They are seething with quantum fluctuations. Ripples appear and disappear constantly, borrowing energy from nowhere and paying it back so quickly that the universe does not have time to notice. These temporary ripples are called virtual particles. They pop into existence, last for an incredibly tiny fraction of a second, and then vanish back into the field from which they came. They are real in the sense that they have measurable effects. They affect the properties of real particles. They shift energy levels in atoms by tiny amounts. They create a force between particles, a force that can be measured and calculated. But they are not permanent. They are not things you could hold on to. They are the foam on the surface of the quantum ocean, rising and falling, always there but never staying. This means that empty space is not empty. It is not a void. It is a place of immense activity, of constant creation and annihilation, of energy that is always there in potential form. The vacuum of space, the absence of everything, is actually full. It is full of fields and fluctuations and virtual particles. It is full of possibility, and this is one of the most beautiful and strange ideas in all of physics. The nothingness you imagine when you think of empty space is an illusion. There is no such thing as truly empty space. There is only the quantum ocean, sometimes calm, sometimes turbulent, but never still. This brings us to the deepest question: what are the fields themselves made of? Is there another layer beneath them? Is there something even more fundamental? This is where physics is pushing forward right now. Some theories, like string theory, suggest that particles are not ripples in fields, but vibrations of tiny one-dimensional strings. Others suggest that space itself is not continuous, but made of tiny chunks, like pixels on a screen. No one knows yet. The fields are the most complete description we have, but they may not be the final answer. They may be the deepest layer we can currently see, but there could be something even deeper, something we have not yet imagined. But for tonight, you do not need to go that far. You do not need to solve the ultimate mystery of existence. You only need to know that the world is stranger and richer than it appears. The things you can see, the solid objects around you, the light in the room, your own body, all of it is made of ripples in invisible fields that fill the universe. You are not separate from those fields. You are made of them. The electrons in your body are ripples in the electron field. The atoms they orbit are held together by ripples in other fields. The energy that keeps you alive flows through fields that extend to the edges of the cosmos. And those fields do not stop at your skin. They continue on, through the walls of your room, through the air outside, through the atmosphere, into space, past the planets, past the stars, out to the farthest galaxies and beyond. There is no boundary. You are connected to everything, not by some mystical force, but by the simple physical fact that the fields that make you are the same fields that make the stars. The same quantum fields are everywhere, and they are the deepest layer of reality we have ever touched. So when you close your eyes tonight, you can think of it this way. The electron field is humming quietly all around you. The photon field is carrying the gentle darkness of your room. The Higgs field is giving you mass, holding you together, making you solid. And deeper still, beyond what we know, the universe is holding possibilities we have not yet even begun to explore. You are part of that. You have always been part of that. The fields have been here since the very beginning, and they will be here long after everything else has gone. And tonight, you can rest in that knowledge. You might have heard the word quantum computing before, and if you have, you probably heard it in a context that made it sound like something from science fiction. A computer that is more powerful than anything that has ever existed. A computer that can break all the codes, solve problems in seconds that would take a normal computer longer than the age of the universe. And all of that is true, in a way. But the deeper truth is even quieter and stranger. A quantum computer is not just a faster computer. It is a different kind of machine entirely, built on the strangeness you have been learning about all night. And the strangest part of all is that it uses superposition and entanglement, the very same things that make the quantum world so hard to grasp, and turns them into tools. Let us start with the computer you already know, the one you might have used today, or the one that is sitting in your pocket or on a desk somewhere. That computer works with bits. A bit is the smallest piece of information a normal computer can handle. It can be one of two things. It can be a 0, or it can be a 1. That is it. Every email you have ever sent, every video you have ever watched, every photograph stored on your phone, all of it is broken down into billions of these tiny decisions. 0 or 1. Off or on. Yes or no. The computer processes these bits one after another in long sequences, and it does this incredibly fast, billions of times a second. But at its heart, it is a simple machine. It follows rules. It takes a bit, looks at it, decides what to do with it, and then moves to the next bit. It is like a person walking down a hallway and opening one door at a time. A quantum computer works with something called a qubit. A qubit is different. A qubit is not limited to 0 or 1. Because of superposition, A qubit can be 0 and 1 at the same time. It can be both simultaneously. It can be 0, it can be 1, and it can be any blend of the two. This is not just a clever way of saying it can switch between them quickly. It genuinely exists in both states at once, until the moment it is measured. And when you put many qubits together, something remarkable happens. The number of states they can hold grows exponentially. 2 qubits can hold 4 states at once. 3 qubits can hold 8. 10 qubits can hold over 1,000. A quantum computer with 300 qubits can hold more simultaneous states than there are atoms in the observable universe. Think about what that means. A normal computer has to explore problems one path at a time. If you gave it a maze and asked it to find the exit, it would try one route, reach a dead end, go back, try another route, reach another dead end, go back again. It is patient and fast, but it still goes one way at a time. A quantum computer with enough qubits can explore every path at the same time. It does not walk down one corridor. It floods the entire maze all at once. It is like water finding its way through a network of cracks. It takes every possible route simultaneously, and the correct answer emerges naturally from the flow. This is why quantum computers are so powerful for certain kinds of problems. They do not just calculate faster, they calculate in a completely different way. Entanglement makes all of this even more powerful. When 2 qubits are entangled, they are linked in a way that does not depend on distance. If you change one, the other responds instantly, no matter how far away it is. In a quantum computer, qubits are entangled with each other on purpose. This allows the machine to perform operations on many qubits at once, using their linked states to carry out complex calculations. The entanglement holds the whole system together, so that when you perform a single operation, it affects the entire network of qubits simultaneously. It is like having a team of workers who can all coordinate with each other without ever speaking. They just know what the others are doing, because they are all part of the same whole. This is not science fiction. Quantum computers exist today. They are still early in their development, and they are fragile machines. Qubits are extremely sensitive to their environment. The slightest change in temperature, the slightest vibration, a stray photon of light, and the qubit loses its superposition. This is called decoherence. It is the quantum equivalent of waking from a dream. The delicate balance of possibilities collapses into a single definite state, and all the power of the quantum calculation is lost. To prevent this, quantum computers are kept in specially designed chambers and cooled to temperatures colder than outer space. They are shielded from magnetic fields, from heat, from any form of interference. They are like tiny frozen islands of possibility, suspended in near absolute zero, surrounded by walls of silence. Despite these challenges, progress is happening fast. The number of qubits that can be held in a stable state is growing every year. The time before decoherence sets in is getting longer. Researchers are finding new ways to correct errors that arise during calculations, because in a quantum computer, errors are not just occasional glitches. They are part of the process, and they need to be managed with special quantum error correction codes. These codes use additional qubits to constantly check the state of the main qubits, catching mistakes before they can spread. It is like having a team of editors working alongside a writer, checking every word before it is committed to the page. What will quantum computers actually be used for? There are several areas where their power could change everything. One of the most talked about is cryptography. Much of the encryption that keeps your online information safe relies on the difficulty of factoring very large numbers into their prime factors. A normal computer can do this for small numbers easily enough, but for numbers that are hundreds of digits long, it would take longer than the lifetime of the universe. A quantum computer, using an algorithm called Shor's algorithm, could factor those numbers much faster. This is why governments and banks and technology companies are all paying close attention. A quantum computer powerful enough to break current encryption would change the landscape of digital security. But at the same time, quantum cryptography offers a new kind of security that is fundamentally unbreakable, because it relies on the laws of physics themselves rather than on mathematical complexity. Another area where quantum computers could make a huge difference is in medicine and chemistry. Understanding how molecules behave is one of the hardest problems in science. A molecule is made of atoms, and those atoms interact according to quantum rules. To simulate a molecule accurately, you would need to account for all those quantum interactions, and they quickly become too complex for any normal computer to handle. But a quantum computer, because it operates on quantum rules itself, can simulate molecules directly. It can model how a new drug interacts with a protein in your body. It can predict how a catalyst might speed up a chemical reaction. It can design better batteries, more efficient solar cells, new materials that do not yet exist. This is not just about speed. It is about being able to ask questions that are impossible to ask any other way. There are also applications in logistics and optimization. If you need to find the most efficient route for a fleet of delivery trucks, or the best way to arrange flights at an airport, or how to distribute power across a national grid, those are all optimization problems. They are problems where you need to choose the best option among an enormous number of possibilities. A normal computer can do this for small systems, but for large systems, the number of possibilities grows so fast that even the fastest computers in the world cannot find the best answer in a reasonable time. They have to settle for good enough. A quantum computer could explore all the possibilities at once and find the true optimum. It could save fuel, reduce waste, make supply chains more efficient. It could help manage renewable energy sources across a continent. But it is important to remember that quantum computers will not replace your laptop or your phone. They are not meant for everyday tasks. They are not going to play games or send emails or browse the internet. They are specialized machines designed for very specific kinds of problems. The same quantum strangeness that makes them so powerful for certain tasks makes them useless for others. They are like telescopes. A telescope is incredibly powerful for looking at distant stars, but you would not use one to read a book. Quantum computers will live in laboratories and research facilities, and maybe one day in large data centers. They will be used by scientists and engineers and mathematicians to solve problems that we cannot even imagine solving today. And the results of those calculations, the insights they produce, will eventually find their way into the world in ways we can begin to sense. What is perhaps most beautiful about quantum computing is that it takes the very things that make the quantum world confusing and turns them into something useful. Superposition, which seems to defy common sense, becomes the source of exponential power. Entanglement, which Einstein called spooky, becomes the glue that holds the calculation together. Uncertainty, which limits what we can know about a particle, becomes a resource we can exploit. The strangeness is not a bug, it is the feature. It is the thing that makes all of this possible. Right now, somewhere in a laboratory, a handful of qubits are frozen in their superposition. They are doing nothing and everything at the same time. They are holding all possible answers to a question that no one has even asked yet. And in that tiny frozen space, surrounded by shielding and silence and cold, the universe is doing something it has always done. It is exploring possibilities. It is holding potential. It is waiting for the moment when it will be asked to become something definite. You do not have to understand all of it tonight. You do not have to remember the names or the numbers or the algorithms. All you need to know is that the same quiet strangeness that makes the stars burn and the atoms hum and the particles walk through walls is now being used to think. And like everything else in quantum physics, it is a reminder that reality is deeper, stranger, and more full of possibility than we ever imagined. You have now been on a long journey through the quantum world. You have heard about particles that are waves, waves that are particles, objects that are in two places at once, connections that span the universe, and fields that fill all of space. And through all of this, you might have noticed that there is a question that keeps appearing. A question that none of the experiments, none of the mathematics, none of the discoveries have fully answered. The question is this: what does quantum mechanics actually mean? What is really going on beneath the equations? What is the universe actually doing when no one is looking? This might seem like a strange question. In most of science, you do not ask what things mean. You just ask how they work. You observe, you measure, you predict, you test. That is the scientific method. And quantum mechanics is the most successful scientific theory in history. Its predictions are accurate to more than 10 decimal places in some cases. It has never failed a single experimental test. It works. But the fact that it works does not tell you what it is telling you about reality. The math is clear. The interpretation is not. And physicists have been arguing about this for almost 100 years. The most common interpretation, the one you are most likely to hear in a physics classroom, is called the Copenhagen interpretation. It was developed in the 1920s by Niels Bohr and Werner Heisenberg and their colleagues in the city of Copenhagen. The Copenhagen interpretation says that quantum mechanics is a tool for predicting probabilities. It does not try to tell you what a particle is before you measure it. It does not try to describe reality when no one is looking. It simply says that the wave function, that mathematical object you learned about earlier, contains all the information you can know about a particle. And when you make a measurement, the wave function collapses into a single definite outcome. Before that measurement, the particle does not have a definite position or speed or spin. It has all of them simultaneously, until the act of observation forces it to choose. Bohr argued that this is not a limitation of our knowledge. It is not that the particle has a definite state and we just do not know what it is. He said that the particle genuinely does not have a definite state before measurement. The act of measurement creates the definite state. The observer and the observed are part of a single system. You cannot separate the measurement from the thing being measured. This is called complementarity. It means that the way a particle behaves depends on what you are asking it to do. If you ask it to behave like a wave, it will. If you ask it to behave like a particle, it will. But it is not either one until you ask the question. The Copenhagen interpretation is pragmatic. It says, do not ask what the particle is really doing when you are not looking. That question has no answer. Just calculate the probabilities and move on. For many physicists, this is perfectly satisfying. They use the mathematics, they get the right answers, they build lasers and transistors and MRI machines. They do not need to know what reality is doing behind the scenes. The theory works, and that is enough. But for others, this feels deeply unsatisfying. It feels like a surrender. It feels like saying you do not care about the nature of reality, only about the measurements you can make. And some people, very intelligent people, have spent their entire careers trying to find a deeper explanation. One of the most famous alternatives is the many worlds interpretation. This was proposed by Hugh Everett in 1957. Everett was a graduate student at Princeton, and he looked at the mathematics of quantum mechanics and asked a simple question. What if the wave function never collapses? What if the collapse is an illusion? What if, instead of collapsing into one outcome, the wave function simply branches? Every time a quantum measurement happens, every time a particle is observed, the universe splits into multiple copies. One copy for each possible outcome. In one universe, the particle was spin up. In another universe, it was spin down. Both are equally real. Both actually happen. There is no collapse. There is just branching. This is a mind-bending idea. It means that there are countless versions of you, reading countless versions of this script, in countless parallel universes. In some of them, you fell asleep already. In some of them, you are still awake. In some of them, you made different choices earlier in your life. Everything that could happen does happen, somewhere in the branching tree of reality. The universe does not choose one outcome over another. It takes all of them. And the reason you only experience one is that you are just one branch. You are one version of yourself among an infinite number, all equally real. For many people, the many worlds interpretation is either liberating or terrifying. It removes the mystery of collapse, but it replaces it with the mystery of infinite branching universes. It is elegant in its way, because it follows the mathematics without adding anything extra. It does not need a collapse mechanism. It does not need an observer to create reality. The wave function just keeps evolving, forever, and the universe keeps splitting, forever. But it raises deep questions of its own. What does it mean to be a conscious observer in such a universe? What does probability mean if all outcomes happen somewhere? If you are going to win the lottery in some branch, what does it mean to say you have a low probability of winning in this one? There is another alternative called the pilot wave theory, or de Broglie-Bohm theory. This was proposed by Louis de Broglie in the 1920s and later developed by David Bohm. The pilot wave theory says that particles do have definite positions and definite trajectories all the time. They are not spread out as clouds of probability. They are real little objects moving through space. But they are guided by a real wave that exists alongside them. The wave tells the particle where to go. The particle follows the wave, like a leaf floating on a river. The wave guides it, and the particle always has a definite path. The strange thing about the pilot wave theory is that the guiding wave is not something you can see directly. It is hidden. You can only see its effects on the particles, and those effects produce exactly the same probabilities as standard quantum mechanics. So in this interpretation, there is no superposition. The particle is always somewhere specific. There is no collapse. The particle always has a definite state. The uncertainty is not a property of the particle. It is a property of our inability to see the guiding wave directly. The universe is deterministic in this view. Everything follows a definite path. We just cannot predict it because we cannot see all the variables. This is why it is sometimes called a hidden variable theory. The pilot wave theory is appealing to many people because it restores a kind of common sense. Particles are particles. They are where they are. The strangeness is not in the universe. It is in our incomplete knowledge. But the theory has its own costs. It is non-local, which means the guiding wave can affect particles across vast distances instantly. That is the same kind of spooky action that Einstein disliked about entanglement. And the theory requires a special status for the guiding wave, something that does not emerge naturally from the math. For many physicists, it feels like a patch, a way to force quantum mechanics to behave like classical physics, when maybe it just does not. There is also something called relational quantum mechanics. This interpretation, proposed by Carlo Rovelli, says that a quantum state is not a property of a particle by itself. It is a property of the relationship between the particle and the observer. The state of a particle is always relative to the system that is observing it. There is no absolute state. There is no God's eye view of the universe, where everything is known perfectly. There are only relationships between systems. One system measures another, and that creates a definite state relative to that measurement. But another system, measuring the same particle at the same time, might see something different. Both are equally valid. There is no contradiction. There is only a web of relationships, and nothing exists outside that web. This is a deeply philosophical view. It resonates with ideas from ancient philosophy and modern physics. It suggests that reality is not a collection of things with fixed properties. It is a network of interactions, each one creating a temporary reality for the participants. The universe is not a machine running on a single script. It is a vast, ongoing conversation between systems, and each conversation is real for the systems involved. So which interpretation is correct? The honest answer is that no one knows. Physicists are split. There are passionate defenders of each view. There are experiments being designed that might distinguish between some of them. For example, there are tests of Bell's inequalities, which you might remember from the section on entanglement. These tests have ruled out certain types of hidden variables. They have shown that any theory with local hidden variables, variables that are only affected by things in their immediate vicinity, cannot reproduce the predictions of quantum mechanics. The pilot wave theory is non-local, so it survives those tests. But other hidden variable theories have been ruled out. There is also ongoing work on the measurement problem. What causes the wave function to collapse? Is it really an observer, or is it just any interaction with a large system? There are theories that try to explain collapse as a physical process, a real event that happens when a certain threshold of mass or complexity is reached. These are called collapse models. They add new terms to the equations of quantum mechanics, terms that cause the wave function to collapse naturally over time. The collapse happens faster for large objects, which is why everyday objects are always definite, while tiny particles can remain in superposition for a long time. These models make testable predictions, and experiments are currently looking for those predictions. But for all this debate, there is one thing everyone agrees on: the mathematics works. Quantum mechanics is incredibly accurate. It has revolutionized our understanding of the universe and our ability to manipulate it. The interpretations are fascinating, and they matter deeply to the question of what reality is, but they do not change the predictions. Whether you believe in the Copenhagen interpretation, or the many worlds, or the pilot wave, or something else entirely, you will still get the same answers when you calculate the behavior of an electron or the spectrum of a star. This brings us to a quiet and important truth. The universe does not require you to choose an interpretation. It does not require you to understand the debates, or even know they exist. The flowers bloom, and the stars burn, and the atoms hum, according to rules they have never needed to explain. They have been doing their quantum dance for billions of years, long before humans existed, long before anyone asked what it all meant. And they will keep doing it long after we are gone. You do not have to resolve the deepest mystery of existence tonight. You do not have to pick a side. You do not have to understand the wave function or collapse or branching universes. You only need to know that the universe is beautiful and strange and full of questions that still have no answers. That is part of its beauty. That is part of the quiet wonder of being alive. The physicists will keep arguing. The experiments will keep running, and the universe will keep being itself, indifferent to our debates, patient with our ignorance. So close your eyes if they are not closed already. Let your breath slow. The questions will still be there in the morning, but for tonight they can wait. The universe was here before you were born. It will be here after you are gone. And right now, in this moment, it is holding you in its quantum embrace. You are made of fields and probabilities and relationships, and you are exactly where you need to be. You have come a long way tonight. Through atoms and energy packets, through waves that are particles and particles that are waves, through double slits and uncertainty and entanglement. You have traveled to the edge of what we know and looked out at what we do not. And now, in this final part of the journey, it is time to step back and simply feel the shape of it all. Not to review, not to remember, but to rest in the quiet understanding that you are part of something vast and strange and deeply beautiful. The universe is not a machine. That is perhaps the most important thing to carry with you as you drift towards sleep. For centuries, scientists thought of the cosmos as a great clockwork device. You could wind it up and it would run predictably forever, every gear turning exactly as it should. Newton's laws seemed to describe a universe that was orderly, deterministic, knowable. If you knew the position and speed of every particle at one moment, you could predict every future moment with perfect accuracy. The universe was like a giant equation, and all you had to do was solve it. But quantum physics shattered that image. The universe is not a clock. It is something more like a dream. At its deepest level, it is made of possibilities, not certainties. Particles do not follow predetermined paths. They exist as clouds of probability, spread out across space, holding all their potential futures at once. They are not objects in the classical sense. They are tendencies. Tendencies to be here or there. Tendencies to do this or that. And only when the universe pays attention, only when something interacts with them, do they become definite. The universe is not written in stone. It is written in potential, in the endless shimmer of things that might happen. This is not just a philosophical idea. It is the most accurately tested theory in the history of science. The mathematics of quantum mechanics has been confirmed to more decimal places than any other physical theory. It describes everything from the glow of a neon sign to the fusion inside a star to the chemical bonds that hold your body together. It works. And what it tells us is that reality is not what it appears to be. The solid ground beneath you is not solid. It is mostly empty space, held together by forces that are carried by invisible ripples in invisible fields. The light that reaches your eyes is not a continuous stream. It is a rain of tiny packets, each one carrying a fixed amount of energy. The atoms that make up your body are not tiny solar systems. They are quantum clouds, buzzing with energy, obeying rules that would make no sense to anyone who had not seen the math. And yet, despite all this strangeness, the universe is coherent. It holds together. The same rules that govern a single photon govern the fusion that powers the stars. The same quantum principles that allow an electron to tunnel through a barrier allow the sun to shine. The same uncertainty that makes the microscopic world fuzzy makes the macroscopic world stable. Everything is connected, not by some mystical force, but by the simple fact that it all follows the same deep laws. The quantum rules are universal. They apply everywhere, to everything, at all times. The universe is not a collection of separate things. It is a single whole, governed by a single set of principles, and those principles are quantum. You are part of that whole. You are made of atoms whose electrons follow quantum rules. The carbon in your cells, the oxygen in your lungs, the calcium in your bones, all of it was forged in the hearts of stars, and all of it is held together by quantum forces. The same entanglement that links particles across the universe links the atoms in your body. The same superposition that allows an electron to be in two places at once is part of the deep structure of your existence. You are not an observer standing outside the quantum world, looking in. You are part of it. You are made of it. You are a quantum object, as much as any photon or electron. And here is something else that is worth sitting with. Human beings discovered all of this in roughly 100 years. From Max Planck's first proposal of the quantum in 1900 to the discovery of the Higgs boson in 2012, our understanding of the deepest layers of reality expanded faster than at any other time in history. In a single century, we went from thinking the atom was a solid ball to understanding that particles are ripples in fields that fill the universe. We went from wondering what stars were made of to reading the chemical fingerprints of galaxies billions of light years away. We went from having no idea how the sun burned to knowing that its fire depends on quantum tunneling, on particles walking through walls. The people who built this understanding were not trying to make money. They were not trying to win wars or gain power. They were trying to understand the universe, because it was beautiful and mysterious. Planck was a quiet, conservative man who did not fully believe his own discovery at first. Einstein was a patent clerk who wrote his most revolutionary papers in his spare time. Bohr was a philosopher as much as a physicist, always asking what the equations were telling us about the nature of reality. Heisenberg was young and intense, wrestling with the limits of what we can know. Schrödinger was a poet at heart, whose equation describes the evolution of possibility with breathtaking elegance. Dirac was silent and strange, whose work revealed the existence of antimatter before it was ever observed. Feynman was a showman and a genius, who said that the double-slit experiment contains the only real mystery of quantum mechanics. They did not agree with each other. They argued passionately, sometimes bitterly. Einstein never accepted quantum mechanics as complete. He spent the last decades of his life trying to find a deeper theory that would restore determinism. Bohr argued with him for years, defending the Copenhagen interpretation, insisting that the observer and the observed are inseparable. Schrödinger hated the Copenhagen interpretation so much that he invented his famous cat thought experiment to show how absurd it seemed. And yet, despite all their disagreements, they were all driven by the same thing: a deep love of the truth, a willingness to follow the evidence wherever it led, a sense of wonder that never left them, even when they were old and tired and frustrated. That sense of wonder is still there, in every physicist who works today. It is there in the researchers trying to build quantum computers, in the astronomers reading the light of distant stars, in the theorists wrestling with the mathematics of string theory and loop quantum gravity. It is there in the students learning quantum mechanics for the first time, their minds struggling to accept what the equations are telling them. It is there in the engineers who build the detectors and the accelerators and the lasers. The wonder is the engine, the beauty is the goal. And now, in this quiet moment, that wonder can be yours. You do not have to understand the mathematics. You do not have to pass an exam or solve a problem. You only have to feel the shape of it. The universe is vast and strange and deeply beautiful. It is made of possibilities and probabilities and relationships. It is not separate from you. You are part of it, in the most literal sense. The atoms in your body were once inside stars. The energy that flows through you is the same energy that flows through the cosmos. The quantum rules that govern the smallest particles govern the molecules in your cells, the air in your lungs, the light that reaches your eyes. Right now, as you lie here in the dark, the atoms in your body are doing what they have always done. They are existing in their quiet quantum way. They are uncertain, spread out in their wave functions, holding all their possible positions and states. They are entangled with each other, connected in ways that span the distances between them. They are tunneling through tiny barriers, particles walking through walls on scales too small to see. They are humming with the energy of the fields that fill all of space. They are not separate from the universe. They are the universe in one of its countless forms. And the universe is paying attention, not in the way a person pays attention, not with consciousness or intention, but in the sense that every interaction, every measurement, every moment of existence is a moment of becoming. The wave functions collapse, the possibilities resolve, the universe becomes definite in one place and one time. And that act of becoming, that constant unfolding, is what holds you together. It is what keeps your atoms from flying apart. It is what allows your cells to function, your blood to flow, your breath to move in and out. The universe does not need to be aware of you to sustain you. It sustains you simply by being what it is. And what it is, at its deepest level, is a vast, seething, beautiful quantum dance. So tonight, let the questions go. Let the details slip away. You do not need to remember the names or the dates or the equations. You do not need to understand superposition or entanglement or the measurement problem. All you need to know is that the universe is stranger and more beautiful than you ever imagined, and you are part of it. You have always been part of it. Every particle in your body has been connected to everything else since the very beginning, since the first moments of the universe, since the atoms were forged in the fires of stars and scattered across the cosmos. You are made of stardust and quantum fields. You are a wave of probability that became a person. You are a momentary concentration of the same energy that fills the entire universe. And tonight, that is enough to know. You do not have to solve any mysteries. You do not have to answer any questions. You only have to rest and let the universe hold you the way it has held everything else since the very beginning. So let your breath slow. Let your body sink deeper into the surface beneath you. The night is quiet, and the universe is vast, and you are exactly where you need to be. There is nothing to do. There is nothing to figure out. There is only the gentle rhythm of your breathing, the soft darkness around you, and the quiet hum of the quantum world, doing what it has always done, carrying you gently, effortlessly, into sleep.